Imagine a world where movement is an illusion, where you can never reach your destination, no matter how hard you try, where every step you take is infinitely sliced into smaller and smaller pieces until you're trapped between motion and stillness. Welcome to the haunting logic of Zeno's paradoxes, arguments so clever, so disturbing, that they've echoed across more than 2,000 years of science, mathematics, and philosophy. Zeno of Elea was not a physicist. He wasn't a scientist by modern standards. He was a philosopher, a student of Parmenides who famously argued that all change is an illusion and that reality is one, unchanging, eternal. To defend this radical idea, Zeno proposed a series of paradoxes that would go on to trouble the greatest minds in history, from Aristotle to Newton, from Einstein to Stephen Hawking. The most famous of Zeno's paradoxes is the paradox of Achilles and the tortoise. Imagine a race. The swift Achilles gives a slow-moving tortoise a small head start. Logically, you'd think Achilles would quickly overtake the tortoise, but Zeno invites us to look closer. In the time Achilles runs to the tortoise's starting point, the tortoise moves forward a little. When Achilles covers that new distance, the tortoise again moves slightly ahead. This happens again and again. Every time Achilles reaches where the tortoise was, the tortoise has moved. No matter how fast Achilles runs, he's always playing catch-up. And if you continue this reasoning indefinitely, it appears Achilles will never overtake the tortoise. He'll get closer and closer, but always remain behind. Infinity stands between them. Another paradox, just as unsettling, is the dichotomy paradox. Before you can walk a mile, you must first walk half a mile. But before you walk half a mile, you must walk a quarter mile. Before that, an eighth, and so on. Zeno divides any journey into an infinite number of steps. And here's the terrifying twist. How can you complete an infinite number of steps in a finite amount of time? How can motion even begin if an infinite number of tasks must be completed first? Then there's the arrow paradox. Zeno asks you to freeze time, just for a moment. At any single instant, an arrow in flight is motionless. It occupies a space equal to its length, at rest, frozen in time. But if every instant is a motionless snapshot, how can adding up all these snapshots result in motion? How can movement arise from stillness? These paradoxes, at first glance, might seem like word games, clever tricks, but they dig at something far deeper. They expose a fracture between how we experience reality and how we try to describe it with logic. When Zeno laid out these ideas, mathematics wasn't equipped to deal with infinity. Calculus had not yet been born. Time and space were mysterious, unmeasured terrains. It wasn't until nearly 2,000 years later that mathematicians like Newton and Leibniz developed calculus, tools that allowed us to sum infinite series and quantify motion in terms of limits. Using calculus, we can show that the infinite steps in Zeno's paradox do not require infinite time. The total time Achilles takes to catch the tortoise, or the total distance walked by someone completing infinite halves, adds up to a finite number. Infinity in this context becomes tame, a series that converges. But does that solve the paradox entirely? Not quite. Modern physics reintroduces some of the mystery. Quantum mechanics teaches us that at the smallest scales, space and time may not be infinitely divisible. There may be a minimum length, the Planck length, below which space as we know it ceases to exist. Similarly, there may be a smallest unit of time, the Planck time. If true, this means Zeno's infinite divisions are impossible, not because of math, but because of the nature of the universe itself. Space and time might be digital, not analog, not smooth, but pixelated. And yet, Zeno's ghost lingers. In the field of computation, we find echoes of his reasoning. Algorithms that try to solve problems through infinite iterations bump against physical limits. In artificial intelligence, recursive processes challenge the boundary between the finite and infinite. Even in cosmology, the idea of infinite regress, one event causing another and another forever, raises troubling questions. Zeno's paradoxes are not just puzzles, they are warnings. They remind us that the universe might not always conform to human intuition. Think of an escalator that you're walking up. What happens if the steps get shorter and shorter, endlessly, while the escalator keeps going? You keep walking, but never arrive. Zeno has designed a trap, not to trick us, but to enlighten us. His paradoxes force us to ask, what is motion? What does it mean to move from A to B? If we can't describe it in finite steps, does it exist? Even with calculus and quantum physics in our hands, we are still dancing with Zeno. Every time you watch a digital clock tick forward, 1 second, then the next, you experience time as discrete. But between those ticks, does time flow? Is there a moment in between? Or is that an illusion, a mental fabrication? Zeno's paradoxes remain relevant because they challenge not just science, but perception itself. They haunt the intersection of philosophy, math, and physics. They remind us that no matter how far science advances, some questions will always remain at the edge, unanswered, perhaps unanswerable. So the next time you walk across a room or reach out to grab something, pause and think. Somewhere, deep in the folds of logic and reality, Zeno is whispering, are you really moving? Or are you just getting closer, forever closer, to something you'll never quite reach? There is a silent contradiction that lies deep within the laws of motion, so quiet that even seasoned physicists sometimes miss it. It sits in the realm of fluid mechanics, cloaked in equations that seem perfect, elegant, and complete. But the moment we confront it with reality, something breaks. The contradiction has a name: Olbers Paradox. At first, it sounds harmless, almost clinical, but behind that name is a question that slashes at the very trust we place in Newtonian physics. The paradox begins with a simple idea. An object moves through an ideal fluid. The fluid, in turn, flows smoothly around it, perfectly, symmetrically, with no turbulence, no stickiness, no energy loss. Just a pure mathematical flow. We call this an inviscid, incompressible, irrotational fluid, a concept from Euler's equations, which were developed to describe fluid motion without the messy complications of friction or viscosity. Using these equations, Jean-Laurent d'Alembert, a brilliant 18th century mathematician and physicist, made a discovery that shook the foundations of his field. According to the mathematics, a solid body moving at constant velocity through such a fluid experiences no drag force. In other words, the fluid offers no resistance. None. Zero drag. To the casual mind, this might not sound so strange, but in the real world, it's madness, because every day, we see the exact opposite. When you put your hand out of a moving car window, you feel the air pushing against it. When a swimmer slices through water, they feel resistance. When a jet flies through the sky, it burns massive amounts of fuel to overcome aerodynamic drag. The drag is real. It's measurable. It costs energy, time, and money. And yet, the equations, D'Alembert's own calculations, tell us the drag should be zero. How can this be? This isn't a tiny numerical error or a miscalculated constant. This is a direct contradiction between mathematics and reality, a paradox, a silent scream hidden inside the flow of perfect fluids. D'Alembert's paradox tells us something terrifying, that even the most beautiful mathematical models can be completely, fundamentally wrong when describing the world. It highlights a brutal truth. The equations of ideal fluid dynamics are blind to viscosity. They assume the fluid flows without friction, like silk in a vacuum. In this ideal world, the fluid wraps around the object in a perfectly symmetrical way. The pressure in front of the object equals the pressure behind it, and since drag is the result of pressure difference, there is none. Mathematically, the object should sail on forever without slowing down. But this world doesn't exist. In the real universe, all fluids are viscous. They cling, they drag, they resist. No matter how small the viscosity is, it changes everything. It breaks the symmetry. Behind the object, a wake forms. Turbulence, swirling eddies, chaotic motion that devours energy and exerts force. This wake is the source of drag. It's not just a side effect. It's the reason motion through a fluid costs something. So, what happened in D'Alembert's model? He stripped the fluid of its resistance. He made it ideal, flawless, and in doing so, made it lie. For centuries, the paradox haunted physicists and mathematicians. It wasn't until the late 19th and early 20th centuries that people like Ludwig Prandtl began to piece together an answer. The secret lay in a razor-thin region called the boundary layer, a tiny zone hugging the surface of a moving object where viscosity suddenly matters. Within this narrow skin of fluid, all the complexity comes alive. It's here where velocity gradients form, where friction builds up, where flow separates, where turbulence is born. The boundary layer defies the clean, inviscid picture of Euler's equations, and it's precisely this layer that gives birth to drag. So, D'Alembert's paradox isn't just a mistake, it's a warning. It tells us that the real world cannot be fully captured by simplification, that ideal models, no matter how elegant, can mislead us if we ignore the fine print. The drag force we feel in real life doesn't arise from the core of the fluid, but from its skin, from the chaos and asymmetry that math once tried to erase. Think of an airplane slicing through the sky. On paper, in an inviscid world, it should need no engines. It should glide forever, unresisted. But in truth, it must fight every moment to stay airborne. Its engines roar not to move it forward, but to defeat the invisible hands of the air, the turbulence, the pressure drops, the energy loss. D'Alembert saw the flaw, but in his time, there were no tools to resolve it. No Navier-Stokes equations, no boundary layer theory, no wind tunnels. He saw the truth in numbers, but not in nature. And yet, his paradox became a key that opened a door. It forced later generations to ask deeper questions, to build better models, to look beyond perfection. Even today, fluid dynamics is far from complete. The Navier-Stokes equations remain unsolved in the most general case, a challenge so deep that it's one of the 7 Millennium Prize problems. A $1 million question, still unanswered, still whispering echoes of D'Alembert's paradox. So, the next time you feel the wind push back against your body or watch a boat cut through water with ripples curling behind it, remember the paradox. Remember that a man once looked into the math and saw a world without resistance, and in doing so, helped reveal the hidden, stubborn truths of the one we actually live in. Imagine 2 twins, identical in every way, born within seconds of each other. They grow up side by side, share the same childhood, the same home, the same heartbeat of time. But one day, something extraordinary happens. One twin boards a spaceship, accelerates to near the speed of light, and leaves Earth behind. The other stays home, grounded, watching the stars from the safety of gravity. Years pass. And then, reunion. The traveling twin returns. But something is off. One twin has aged, the other has barely changed. They were once mirrors of each other. Now one looks into the eyes of a sibling from another era. The traveler is younger. And so unfolds one of the strangest, most debated consequences of Einstein's theory of relativity, the twin paradox. At first glance, it seems like a violation of logic. If motion is relative, shouldn't both twins see the other as moving? Shouldn't each one think they are the one at rest, and the other is aging more slowly? And if that's the case, how can there be a difference at all when they reunite? It feels like time has betrayed symmetry. But the betrayal isn't of physics, it's of intuition. To understand the twin paradox, we must dive deep into the heart of special relativity, a world where time is not absolute, where simultaneity is an illusion, and where speed reshapes the very rhythm of reality. Einstein's special relativity tells us that the faster you move through space, the slower you move through time, relative to someone at rest. This is time dilation. When the twin in the spaceship accelerates to a significant fraction of the speed of light, say 90%, time for them begins to tick more slowly relative to the twin left behind on Earth. And this isn't just some mathematical trick. It's been tested. Muons, tiny subatomic particles created in Earth's upper atmosphere, should decay before ever reaching the surface. But because they're moving at relativistic speeds, time for them slows down. They survive long enough to be detected at ground level. Their lifespan stretches, not because they change, but because time itself bends to velocity. The same thing happens to the traveling twin. Inside the spaceship, a clock ticks slowly. Heartbeat, breath, cell division, all stretching subtly as the ship rockets forward. But the paradox doesn't fully bloom until the turnaround. Because here's the crux. Motion is relative, yes, but acceleration is not. The twin on Earth remains in an inertial frame, unaccelerated, constant. But the traveler breaks this symmetry. When the spaceship turns around to return to Earth, it decelerates, then accelerates in the opposite direction. That moment of turning, of feeling gravity-like forces press them into the seat, that's where the symmetry shatters. It's in that moment the traveler's frame shifts. They move from one inertial frame to another, and in doing so, their perception of simultaneity, the now they assign to distant events, jumps From the perspective of special relativity, this shift accounts for the sudden leap in the age they attribute to the Earth-bound twin. So when the traveler returns, less time has passed for them. Not because of a contradiction, but because one twin changed frames and the other did not. Still, the implications are staggering. Time, once thought universal, becomes personal. Each path through space-time is unique. Each velocity shapes how fast or slow the future arrives. The paradox reveals this not as a bug, but as a feature of the universe. The math supports it. The longer, straighter path through space-time, the Earth twin's path, results in more elapsed time. The curved, accelerated path, the traveler's, leads to less. This isn't about perception, it's about what actually happens. Atomic clocks flown around the world on airplanes have verified it. The clocks moving at speed return slightly behind their stationary twins. The effect is small at everyday speeds, but at relativistic speeds it becomes profound. Think about what this means. In theory, we could send a spacecraft on a journey to a star system 25 light-years away at near-light speed. From Earth's perspective, the trip might take over 50 years round trip. But for the travelers aboard that ship, it might feel like only a few years. They had returned to a world that aged without them, generations older, friends gone, history moved on, and they remain young. In science fiction, this concept powers countless stories: interstellar travel, suspended time, ageless wanderers. But the paradox is no fantasy. It's a glimpse into how time actually works. A reminder that we are not passengers in time, but participants. That the universe does not give us one clock, one pace, one present, but many. It forces us to ask, what is time? Is it simply what ticks on our wrists? Or is it deeper? A path carved through the fabric of reality, shaped by speed, shaped by motion, shaped by choice. The twin paradox doesn't undermine relativity, it reinforces it. It's a mirror held up to our assumptions, cracking them one by one until what's left is not confusion, but clarity. One twin went to the stars, one stayed home. But it was never about distance, it was about time, and how, in the hands of Einstein, time becomes not just a backdrop for events, but a character in the story itself, malleable, mysterious, and deeply personal. You're standing on a stage, bright lights, a cheering crowd, and a host in a dazzling suit. Before you are 3 closed doors, door 1, door 2, door 3. Behind one of them is a brand new car. Behind the other 2, goats. The host, Monty Hall, invites you to choose. You think carefully and point to door 1. Monty smiles, but instead of opening your chosen door, he opens another, door 3. Behind it, a goat bleats at you, unfazed by the spotlight. Then comes the twist. Monty turns to you and says, "Would you like to switch your choice to door 2 or stay with door 1? The crowd hushes, tension builds, and in that moment, your brain begins to spiral. It's a 50 chance now, right? 2 doors, 1 car, 1 goat. Switching doesn't matter, does it? This is the Monty Hall paradox, and it has baffled even the brightest minds. Not because the math is hard, but because the truth feels like a lie. Let's break it apart. When you first chose door 1, the odds of it hiding the car were 1 in 3. That's just basic probability. 1 good door, 3 options. So the chance you picked wrong is 2 out of 3. Now, here's the key. Monty knows where the car is. He will always open a door with a goat. He will never reveal the car by accident. That means his action, opening door 3 to reveal a goat, is not random. It's calculated. And that changes everything. When Monty opens door 3, he's giving you information. He's indirectly telling you something about where the car isn't. And in doing so, he shifts the odds, just not in the way most people think. Let's rewind. You had a 1 in 3 chance of choosing correctly. That means there was a 2 in 3 chance the car was behind one of the other 2 doors. But once Monty opens one of those doors and reveals a goat, that entire 2/3 probability condenses onto the remaining unopened door. Switching, then, gives you a 2 in 3 chance of winning the car. Staying gives you a mere 1 in 3. It doesn't feel that way. Our instincts scream, 50, 50. The visual simplicity of 2 doors tricks our brains. But math doesn't care about your feelings. The logic is relentless and correct. To really feel it, let's scale it up. Imagine 100 doors. 1 hides a car. You pick door 1. That's a 1 in 100 chance. Monty, who knows everything, opens 98 other doors, all with goats. Only your door and, say, door 27 remain closed. Now, would you stay? Of course not. Door 1 had a 1% chance. Door 27, by contrast, has become the lone survivor of the 99% chance you were wrong. Monty's choice condensed all of that unlikeliness onto one door. You'd switch in a heartbeat. But when it's just 3 doors, our minds can't help but misjudge. We confuse Monty's knowledge with randomness. We treat his action as neutral, when in fact it is laced with certainty. He's not guessing. He's guiding. Psychologists love this paradox because it shows how the human brain struggles with conditional probability. Our intuition isn't wired for it. Even people with degrees in mathematics often fail to get it right without careful analysis. When Marilyn Vos Savant, once listed as the world's smartest woman, published the solution in a popular magazine, she received thousands of angry letters, including from mathematicians and PhDs, telling her she was wrong. But she wasn't. She was just ahead of the curve. And this paradox reaches beyond game shows. It touches real life. Every day we make decisions with partial information. We weigh risks, we see outcomes. And like Monty, the universe sometimes reveals just enough, but only if we're paying attention. It teaches us a deeper lesson. Not all uncertainty is equal. Some chances can be shifted. Some risks can be optimized. But only if we understand the rules behind the curtain. Monty Hall wasn't just running a game, he was offering a challenge to see past the illusion of choice, to embrace the strange logic of probability, and to recognize that in the theater of chance, knowledge is power. The car doesn't go to the luckiest, it goes to the wisest, the one who sees the game for what it really is. Imagine a time traveler who, in a moment of wonder, decides to visit the past. Their goal? To visit a brilliant physicist, someone whose ideas will change the world. But there's a twist. A peculiar item, a book, one that was never written by the time traveler, is what sparks the scientist's inspiration. And here's where the paradox kicks in. The book is a work of fiction, written by none other than the time traveler themselves, using the knowledge gleaned from the future. The time traveler gives the book to the physicist, and in the years that follow, the scientist writes the theories that change history. These theories, of course, will include the existence of time travel itself, and eventually the time traveler will be able to go back in time, where the cycle begins anew. But the book has no true origin. It's just passed back and forth, from future to past to future, with no clear point of creation. This is the Bootstrap Paradox, a mind-bending concept where cause and effect loop around endlessly, creating a situation where the origin of an object, an idea, or even a person is entirely untraceable. It's like a puzzle with no solution, a loop that defies traditional concepts of time, causality, and reality. At the heart of the Bootstrap Paradox lies the core question. If something has no origin, then how can it exist at all? Let's explore this with an example that might sound familiar. Imagine you are in a time machine. You travel back to 1950 and find a young Isaac Newton, the famed physicist, struggling with his understanding of the laws of motion. In a moment of generosity, you hand him a copy of your physics textbook. Newton reads it, is inspired, and from that moment, the foundations of modern physics are laid out in Newton's own writings. Fast forward to the present, and you, as a time traveler, have used Newton's laws to build the very time machine that allowed you to travel back to him. In a sense, Newton's laws of motion are responsible for your time machine. Yet, you wouldn't have had those laws in the first place if you hadn't traveled back to give them to him. So, what is the source of this knowledge? Who wrote the laws of motion? Newton, inspired by you, or you, inspired by Newton? The knowledge seems to exist in a loop, creating a paradox where the origin of information, or even the existence of the time machine, is tied to itself. There's no starting point, no moment in time where the knowledge was first discovered or created. It just is. In this paradox, time and causality blend into something incomprehensible. Traditional cause and effect becomes meaningless. We often assume that for something to exist, or to have meaning, it must originate from somewhere. We assume that the past gives birth to the present, and the present determines the future. But in the Bootstrap Paradox, time is no longer linear. It's cyclical, recursive, a loop that can't be untangled. The Bootstrap Paradox also challenges the very idea of time travel. If you could go back and give an idea or an object to someone in the past, you would essentially be creating a reality where that idea or object exists outside of any initial cause. This creates a reality where the past and future are intertwined in a way that seems to break the laws of physics, where one event feeds into another endlessly without a point of origin. But this paradox isn't just a thought experiment. It has been explored in science fiction for decades. In the world of movies and books, time travelers often find themselves tangled in these loops. In one of the most famous examples, the Doctor Who series has featured episodes where a time traveler hands Shakespeare a copy of his own works, or where a musician gets inspiration for a hit song from their future self. The Bootstrap Paradox is a true test of our understanding of causality. How do we define the origin of something that can exist without being created? It forces us to question the foundation of time itself. Does time follow a linear path, as we often believe? Or is time more like a loop, where events can repeat endlessly, each iteration feeding the next? The deeper we dive into the paradox, the more we begin to understand that our conventional notions of time, linear, directional, are only one possible interpretation. The Bootstrap Paradox suggests that time might be much more flexible, fluid, and complicated than we can ever truly grasp. Moreover, the paradox also raises questions about free will. If events can exist without clear origins, does that mean they are fated to happen? Are we simply actors in a play, playing our roles in an already written script? Or can we truly make choices, breaking free from the loops of predestination? Some have argued that the Bootstrap Paradox can never occur in reality, as it leads to logical contradictions. In a world governed by the rules of classical physics, the paradox might seem impossible. But in the realm of quantum physics, where particles behave in strange, non-intuitive ways, the Bootstrap Paradox becomes a possibility worth considering. In the quantum world, particles can exist in multiple states at once, and the concept of time itself is much more uncertain. Perhaps, in this strange domain, a loop like the one described in the paradox could somehow be true, even if we can't fully grasp the implications of the Bootstrap Paradox. It reminds us that our understanding of time and causality is still very much incomplete. The paradox invites us to look at the universe with fresh eyes, to embrace the strange, to question the foundations of reality itself. And perhaps, just perhaps, the next great scientific discovery will be one that gives us a glimpse into the truth behind this paradox. Until then, we are left to wonder, what if everything we know about time is just the beginning of something much bigger? Time travel has captured the imagination of humanity for centuries. The thought of stepping into a machine, traveling backward or forward through time, and observing, or even altering, the course of history is a tantalizing one. But, as thrilling as it is, time travel presents paradoxes that challenge the very fabric of reality. One of the most well-known and perplexing is the grandfather paradox. The concept is simple. You travel back in time to a point before your grandfather had children. In a moment of tragic irony, you prevent him from meeting your grandmother, or perhaps you accidentally cause his death. Without your grandfather, your parent, your father or mother could never have been born, and by extension, neither could you. But here's where the paradox unfolds. If you were never born, then how could you have traveled back in time to kill your grandfather in the first place? It's a loop. It's a contradiction that seems to tear apart the very foundation of causality. The question echoes through time. How can your past actions prevent your very existence when those actions were supposed to be the result of your existence? Let's take a deeper dive into this paradox. You are born, live your life, and one day, you decide to invent or discover time travel. With this newfound ability, you travel back to a moment before your grandfather met your grandmother, and in a desperate or unintended series of events, you cause your grandfather's death. Now, your father or mother never exists, and by extension, neither do you. But if you never existed, then how could you have traveled back in time? How could you have killed your grandfather? The very act of traveling to the past to change history should, in theory, be impossible, because your very existence hinges on that history occurring in the first place. Your life is a consequence of the events you are trying to undo. At first glance, the grandfather paradox seems to suggest an unsolvable contradiction in the fabric of time. If the timeline is mutable, and if actions taken in the past can alter the future, then paradoxes like this one seem inevitable. The past and the future are connected in a delicate balance. But what happens when one piece of that puzzle is erased? The grandfather paradox is not just a thought experiment for philosophers or physicists. It challenges our core understanding of cause and effect. In our daily lives, we assume that events follow a linear progression. An effect follows a cause. But in the world of time travel, this order seems to break down. If actions taken in the past can unravel the future, then we're left with a world where free will becomes meaningless, where even the most fundamental laws of physics could be upended. Some scientists argue that this paradox presents a flaw in the very notion of time travel. If the timeline is mutable and actions in the past can change the future, it suggests that the past isn't fixed. This leads to an unsettling possibility. If the timeline can be altered, what's to stop a time traveler from changing history in a way that causes a paradox, rendering time travel itself impossible? But there are theories that try to resolve this paradox. One such theory is the many worlds interpretation of quantum mechanics. According to this theory, every time a time traveler alters the past, they don't actually change the future. Instead, they create a new branch of reality, a new timeline where their actions take place, while the original timeline remains intact. In this interpretation, the grandfather paradox doesn't exist because the time traveler's actions create an entirely new parallel universe. In one universe, the time traveler prevents their grandfather's death, and in another, they never existed at all. Each timeline exists independently, and the paradox is avoided because no single timeline is ever altered in a way that causes a contradiction. The traveler's actions create a split in the fabric of reality, not a loop of causality. However, even this theory raises new questions. If time travel creates infinite timelines, where do they all go? Do they remain forever separate, or do they somehow converge back into a single reality? And if reality can split into an infinite number of universes, what does that mean for the concept of free will? Are we just actors playing out a script that has already been written, existing on an infinite number of branches? Or is there still room for genuine choice? Another theory suggests that self-consistency is the key. This theory, known as the Novikov self-consistency principle, argues that the timeline is inherently self-consistent. In other words, any actions a time traveler takes in the past must be consistent with the future they came from. If a time traveler were to attempt to kill their grandfather, some force, whether fate, luck, or quantum mechanics, would intervene to prevent them from succeeding. This theory has been explored in science fiction as well. In stories like The Terminator, time travel is seen as a force that maintains the integrity of history. In these narratives, even if a time traveler tries to change the past, the events are shaped in such a way that they don't create contradictions. The grandfather paradox is avoided, not by creating alternate timelines, but by ensuring that the time traveler's actions can never truly alter the fundamental events that led to their existence. But is this solution truly satisfying? Does the idea of an unalterable timeline strip time travel of its excitement? Would a timeline that actively prevents paradoxes make time travel a less appealing concept? Perhaps the most intriguing aspect of the grandfather paradox is the way it challenges our perception of time itself. It forces us to question whether time is truly linear or whether it's just a construct, a set of rules that we've created to make sense of our universe. The paradox suggests that if time travel is possible, then perhaps the rules of time are not as fixed as we think. The grandfather paradox is more than just a conundrum about time travel. It's a window into our understanding of reality itself. What happens when cause and effect collapse into one another? What happens when we are no longer able to trace the origins of events? When the past, present, and future are all mixed together in an eternal loop? At its core, the grandfather paradox is about the limits of human understanding. We are bound by the concept of linear time, but what if that isn't the whole story? What if time is just another piece of a much larger puzzle that we are only beginning to comprehend? The concept of time travel has long intrigued philosophers, physicists, and science fiction enthusiasts alike. One of the most puzzling paradoxes that arises when discussing time travel is the predestination paradox, a mind-bending concept where the past and the future are intricately linked in such a way that events are predestined to unfold exactly as they must. ensuring that a particular sequence of events leads to a fixed outcome. In essence, the predestination paradox suggests that the actions of a time traveler in the past don't create changes in the timeline. Instead, the time traveler's actions were always part of the timeline in the first place. In other words, you don't travel back in time to change history. You travel back to fulfill history. The future is already set in stone, and your presence in the past was always part of the chain of events that led to that future. Let's break this down with an example that's as simple as it is perplexing. Imagine you're a time traveler, and you travel back in time to prevent a catastrophic event from happening. You're trying to stop the assassination of an important figure, perhaps a president or a revolutionary leader. You arrive in the past, and despite your best efforts, the assassination still takes place. Afterward, you realize that your very actions were responsible for ensuring that the event unfolded as it did. You weren't there to prevent the assassination. You were there to make sure it happened. This is the essence of the predestination paradox. You are fated to play a role in events, and no matter what you do, you can't change the ultimate outcome. Your actions are already woven into the fabric of time, and trying to alter events only ensures that they happen in the way they always were meant to. But why does this happen? Why does the future seem to be so rigidly predetermined? To answer that question, we need to look deeper into the nature of time itself. The idea of a predestination paradox challenges our most basic understanding of cause and effect. In our everyday lives, we assume that the future is open, that we can make choices that will shape the world around us. We believe that the future is malleable, subject to the influence of our decisions. But in the world of time travel, this assumption is turned on its head. In a universe governed by the laws of a predestination paradox, the timeline is already fixed. Every event, every action, every choice you make is already written in the grand scheme of things. This means that time travel isn't about changing the past or the future. It's about fulfilling a role that has already been assigned to you. In this view, time is like a river, flowing in one direction, and no matter how much you try to swim upstream, you'll always end up exactly where the current takes you. The idea of the predestination paradox has been explored in various works of fiction. One of the most famous examples comes from the Terminator series. In these films, a future where artificial intelligence has taken over the world is already set in motion, and the time traveler, Kyle Reese, is sent back in time to protect Sarah Connor. However, it is revealed that Kyle Reese's actions lead to the very events that caused the rise of Skynet, the super-intelligent AI. Another example of the predestination paradox can be found in Back to the Future. In the first film, Marty McFly travels back in time and accidentally prevents his parents from meeting, thereby threatening his own existence. As a result, Marty has to make sure that his parents fall in love, which will ensure his own birth. In this case, Marty's efforts to change history are actually part of the reason that history unfolds as it does. His interference in the past ensures that he will continue to exist in the future. In both of these examples, the central idea is clear. Time isn't something that can be changed. It's something that must unfold in a specific way. The events of the past, present, and future are all interconnected, and any attempt to alter one part of the timeline will only reinforce the original sequence of events. The timeline is like a giant, unchangeable loop where every event serves to bring about the next, ensuring that the past, present, and future are locked in a perfect, inevitable cycle. The predestination paradox is a deeply unsettling idea because it challenges the notion of free will. If the future is already written, then what role do we play in shaping it? Are our actions truly our own, or are we simply following a script that was written long before we were born? This question gets to the heart of what it means to be human. We like to believe that we have the power to change our destinies, to make choices that will shape our futures. But in a world governed by the predestination paradox, our choices may be nothing more than echoes of a future that was always meant to be. One of the most profound implications of the predestination paradox is that it suggests a universe where time is not flexible. In this model, time is a static structure, and every action is already accounted for within the timeline. The past and future are not separate or independent. They are two sides of the same coin, eternally interconnected. The future, in this sense, is as immutable as the past. This presents a stark contrast to the view of time that we're accustomed to. We see time as a flowing river, where the future is shaped by the actions we take in the present. But in a universe of fixed events, there is no true flow. There's only the illusion of movement, the appearance of change, when in fact everything is already laid out in a predetermined pattern. If this is true, then what does it mean for the nature of free will and causality? If our actions are fated to happen in a particular way, then do we have any agency at all? Are we merely observers, playing our parts in a grand play whose script was written long before we even had a chance to speak our first lines? The predestination paradox suggests that time travel, rather than offering us the ability to change the past or future, might only reinforce the timeline as it already exists. In this view, time travel isn't a tool for rewriting history. It's a mechanism for ensuring that history unfolds exactly as it must. In the end, the predestination paradox raises more questions than it answers. It forces us to confront the nature of time, causality, and free will. Are we truly free to make choices? Or are we simply acting out our roles in a story that was already written? In a world governed by a fixed timeline, the future may already be set in stone, yet we are left to wonder if there is still room for change, for growth, or for the unexpected. On a quiet afternoon in the summer of 1950, Nobel Prize-winning physicist Enrico Fermi sat with colleagues at Los Alamos National Laboratory. Between conversations about UFO sightings and cartoons, he suddenly asked a question that stunned the group into silence. Where is everybody? That one simple question, uttered almost casually, gave birth to what would become one of the most haunting and perplexing enigmas in modern science, the Fermi Paradox. Let's step back and think about this. The universe is unimaginably vast, billions of galaxies, each containing billions or even trillions of stars. Many of those stars have planets orbiting them, and a significant fraction of those planets are in the so-called habitable zone, the region where conditions might allow for liquid water and perhaps life. By all calculations, the probability that Earth is the only planet hosting intelligent life seems absurdly small, so the natural expectation is intelligent life must have evolved somewhere else. And if so, why haven't we seen any evidence of it? This stark contradiction between high probability and zero evidence is the heart of the Fermi Paradox. Imagine you're looking up at the night sky. Thousands of stars twinkle above, and beyond what you can see lies an ocean of light and time. If just one civilization had managed to develop advanced technology millions of years before us, it would have had plenty of time to spread throughout the galaxy, even traveling at a fraction of the speed of light. The Milky Way is 100,000 light-years across. Yet, in cosmic terms, that's a blink of an eye. With self-replicating probes, or generational starships, or even just slow and steady colonization, an advanced civilization could, in theory, have reached every star system by now. And yet, silence. No signals. No probes. No visits. No artifacts. No whispers in the cosmic dark. Just an unsettling, eerie quiet that stretches from star to star. That's what makes this paradox so chilling. The numbers tell us we should not be alone, and yet all of our telescopes, sensors, and listening posts return the same response: nothing. Scientists have proposed countless theories to try and explain this silence. Some are hopeful, others are terrifying. One possibility is that we are truly alone, or at least the first. Maybe life is much rarer than we think. Perhaps the conditions that allowed life to arise on Earth were incredibly unique. Maybe complex life is the exception, not the rule, and the universe is filled with barren rocks and lifeless oceans. Another possibility is that intelligent life frequently emerges, but destroys itself before it can reach the stars. This idea is often referred to as the concept of the Great Filter. The Great Filter represents a barrier, or series of barriers that prevent life from advancing to a point where it can spread across the galaxy. That filter could be behind us. Perhaps the jump from single-celled organisms to complex multicellular life was the miracle. Or it could lie ahead. Maybe all advanced civilizations eventually succumb to nuclear war, environmental collapse, or artificial intelligence gone rogue. If the Great Filter is ahead of us, the silence of the cosmos may not be peaceful. It may be a warning. Then there's the zoo hypothesis. Maybe aliens are out there, but they're observing us, waiting for us to reach a certain level of maturity before they make contact. Like zookeepers watching animals in a nature preserve. If this is true, we may be surrounded by intelligence, but quarantined in silence. Another chilling possibility? They're out there, and they're hostile. Some scientists suggest that advanced civilizations may avoid broadcasting their existence out of fear. What if there's a predator lurking in the galactic dark, wiping out any civilization that dares to make a noise? Maybe the universe is quiet, not because it's empty, but because it's hiding. Every world that once shouted its presence into the void learned, too late, to stay silent. We must also consider technological limitations. Perhaps alien civilizations communicate using means we haven't yet discovered. Maybe they use quantum entanglement, gravitational waves, or some form of energy we can't yet detect. Or maybe they're so different from us, so unrecognizable, that we wouldn't even recognize their presence if it stood right in front of us. It's also possible that we simply haven't been looking long enough. Humanity has only been sending radio waves into space for about a century. The SETI program, the search for extraterrestrial intelligence, has scanned only a tiny fraction of the sky. Think of it like dipping a cup into the ocean and concluding there are no whales because you didn't catch one in your cup. The universe is vast, and our search has just begun. And still, Fermi's question echoes through time. Where is everybody? The Fermi Paradox isn't just a scientific question, it's a philosophical one. It forces us to confront our own significance, our future, and our place in the grand design of the cosmos. Are we a lone spark of consciousness in a sea of darkness, or are we one among many, waiting for the day when the silence breaks? As we build better telescopes, launch probes deeper into space, and peer into the atmospheres of distant exoplanets, we edge closer to an answer. But until then, the night sky remains a riddle, glimmering, beautiful, and impossibly silent. We listen, we wait, and we wonder. Picture a sealed box. Inside it, a living cat, a small vial of poison, a Geiger counter, a tiny amount of radioactive material, and a hammer. You can't see inside the box. You can't hear what's going on. You have no contact with its contents. And yet, something disturbing is happening within. Something that defies common sense, challenges reality, and fractures the boundary between what we know and what we believe. This is the core of Schrödinger's cat, one of the most famous and most unsettling paradoxes in the history of physics. In 1935, Erwin Schrödinger, a leading figure in quantum mechanics, proposed this thought experiment not to explain quantum theory, but to criticize it. He was disturbed by what the Copenhagen interpretation of quantum mechanics implied about reality, so he designed a scenario so absurd, so deeply uncomfortable, that it would force scientists to confront the consequences of their theories. Here's how it goes. Inside the sealed box is a radioactive atom with a 50% chance of decaying within an hour. If it decays, a Geiger counter detects it. If the Geiger counter goes off, it triggers a mechanism that breaks the vial of poison, killing the cat. If the atom doesn't decay, nothing happens. The cat lives. Now, here's where things get weird. In quantum mechanics, until we observe a particle, it exists in a superposition of states. That is, the radioactive atom is simultaneously both decayed and not decayed. The particle is in limbo, occupying all its possible states at once. And because the fate of the cat is tied directly to the state of the atom, the cat itself must also be in a superposition. It is not alive. It is not dead. It is both alive and dead at the same time, until the box is opened and an observation is made. Take a moment to let that sink in. The cat's very existence, its life or death, depends not just on the events inside the box, but on whether or not you, the observer, choose to look. The observer becomes the decider of reality. In this interpretation, the act of measurement collapses the wave function, forcing the system to pick one state over another. Before observation, there's ambiguity. After observation, reality becomes definite. It sounds ridiculous. How can a cat be both alive and dead? How can a conscious act of observation determine a physical outcome that, presumably, had already happened inside the box? But this is no joke. This is a genuine prediction of quantum theory, a theory that has been proven right again and again in the laboratory. At its heart, Schrödinger's cat reveals a terrifying truth. Quantum mechanics doesn't just describe subatomic particles, it defines how reality works at every level. But our everyday experiences don't reflect that. We never see half-dead cats or people walking through walls, so what gives? This is where the paradox deepens. Some physicists argue that the cat is not actually in a superposition, that the wave function collapses due to interaction with the environment, a process called decoherence. In this view, the cat is either alive or dead long before we open the box, but the superposition exists only in the mathematical formalism. Others go further, saying that all possible outcomes actually happen, but in different universes. This leads to the many worlds interpretation. In one universe, the cat lives. In another, it dies. And you, the observer, also split into two versions of yourself, each witnessing a different reality. But even that solution has its horrors. It suggests an infinite number of branching timelines, where every possible quantum event spawns a new universe. Every breath you take, every blink, every roll of a die fractures reality into countless threads. The world becomes a web of infinite versions of you. Some thriving, some suffering, some watching a cat suffocate in a box. And the questions don't stop there. If observation defines reality, what exactly qualifies as an observer? A human? A camera? A molecule? If conscious minds collapse wave functions, are we somehow entangled with the universe itself? Schrödinger's cat is not just about quantum physics. It's a mirror held up to our understanding of existence. It dares us to confront how little we know about the fabric of the universe. It asks whether reality is objective, or if it only becomes real when we perceive it. It challenges the boundary between life and death, thought and matter, science and philosophy. For nearly a century, physicists and philosophers have debated its implications, and no consensus has emerged. The box remains sealed, the cat remains in limbo, and we, trapped in our own mental superposition, are left to wonder, what is real? And does the universe wait for us to look before it decides? In the silence of that box, the cat holds the answer, but only if you dare to open it. Look up at the night sky. You see stars, countless glittering points of light scattered across the vast darkness. But have you ever asked a very simple, very unsettling question? One that shakes the foundations of everything we believe about the cosmos? If the universe is infinite, eternal, and filled with stars, then why is the night sky dark? That question, so innocent, so childlike in nature, cracks open a paradox that haunted astronomers and physicists for centuries. It's called Olbers Paradox, and it doesn't just ask about the darkness of night. It challenges the very nature of space, time, and the limits of our understanding of the universe. Named after the German astronomer Heinrich Wilhelm Olbers, who formally described the paradox in the 19th century, the question had been whispered long before him. Ancient thinkers wondered about the nature of the stars, but it was only with the growth of scientific cosmology that the real contradiction emerged. If the universe is truly infinite, stretching endlessly in all directions, then every line of sight should eventually land on the surface of a star. Just like if you stood in a forest of infinite trees, no matter where you looked, your vision would be blocked by a trunk. In an infinite universe, the sky should be ablaze. Every square inch should glow with starlight. The entire night sky should be as bright as the surface of the sun. But it's not. Instead, when we look up, we see profound emptiness, vast stretches of inky blackness. Sure, there are stars, but they're scattered like distant sparks in a cosmic void. This contradiction between theory and observation is what gives rise to Olbers' Paradox, and the search for its solution took humanity to the edge of cosmic understanding. For centuries, thinkers offered flawed explanations. Some said interstellar dust was blocking the light, but dust absorbs energy. It heats up. Over time, it would radiate the same amount of light it blocked, so the darkness would still vanish. Others said maybe stars are simply too far away, but that ignores the idea of infinity. No matter how faint a distant star is, in an infinite universe, there are infinitely many such faint stars. Their combined light should overwhelm the darkness. It wasn't until the 20th century that the paradox found its answer, and the answer came not just from astronomy, but from the very structure of the universe. The first breakthrough came from a simple, profound truth. The universe is not static. It's expanding. Thanks to the work of Edwin Hubble and others, we now know that galaxies are moving away from us, and the farther they are, the faster they recede. This means the light from distant galaxies is stretched by the expansion of space. It shifts out of the visible range into the infrared or even microwave region, rendering it invisible to our eyes. So, even though the universe is filled with galaxies, their light doesn't reach us as visible starlight. The expansion hides them from view. But even more crucially, the universe is not eternal. It had a beginning, a moment in time roughly 13.8 billion years ago, the Big Bang. That's when space and time themselves were born. Before that, there was no before, not in any meaningful physical sense. And because the universe had a beginning, that means there hasn't been infinite time for light to travel. Even if stars existed beyond the limits of the observable universe, their light simply hasn't had time to reach us. That's the second key answer to Olbers' paradox. The age of the universe is finite. So, the darkness of the night sky isn't just a mystery, it's a message, a whisper from the very edges of time. It tells us that the cosmos had a birth, that it is dynamic, evolving, stretching, and cooling, that we are surrounded not by infinite ancient light, but by expanding darkness that once blazed with unimaginable energy. In fact, the echo of that blazing past is still around us, not in visible light, but in microwave radiation, the cosmic microwave background. This faint afterglow is the relic of the Big Bang, stretched across the universe by time and expansion. It fills every inch of space. We can't see it with our eyes, but it's there. Proof that the universe once burned with fire and now drifts into darkness. Olbers' paradox was never just about the stars. It was a keyhole through which we glimpsed the true nature of everything. It revealed that we live not in an infinite, static sea of stars, but in a cosmos that had a beginning, and that is heading, slowly but surely, toward a cold, empty end. So the next time you gaze into the night and feel that deep, haunting stillness, remember that darkness is not the absence of something, it is the presence of truth. The truth that the universe is young, that light has boundaries, and that every shadow in the sky is a window into the past. Olbers' paradox asked a question that sounded so simple, and yet led us to the very heart of cosmology. It transformed our understanding of time, of space, and of the fragile flicker of light in an ocean of nothingness. The stars are out there. The night remains dark. And in that darkness, we found the edge of the universe. Imagine two containers, side by side, each filled with a gas, say oxygen, at the same pressure, volume, and temperature. A wall separates them. Now, imagine removing that wall, allowing the gases to mix. It seems straightforward, even boring. But suddenly, physics throws a paradox into your hands, something so quietly bizarre that it forces us to rethink how we define entropy, identity, and the very idea of difference. This is the haunting riddle known as Gibbs Paradox. At first glance, it feels like there's nothing paradoxical. Remove the partition and the gases spread out. If the two gases are different, oxygen on one side, nitrogen on the other, we expect entropy to increase. That makes sense. Entropy is, after all, the measure of disorder, or, more precisely, the number of microscopic configurations that result in the same macroscopic state. So, when different gases mix, the number of possible configurations increases. The disorder increases. Entropy increases. All good so far. But here's where the paradox comes in. What if both gases are not different? What if they're exactly the same? Same molecule, same temperature, same everything. According to classical thermodynamics, even then, the entropy should increase when the wall is removed because the molecules have more space to move. But hold on. If nothing has fundamentally changed, if the final state is indistinguishable from the initial one, why should entropy increase at all? This is the core of Gibbs' paradox. If we treat identical particles as distinguishable, then mixing even identical gases leads to an increase in entropy. But that doesn't make sense physically. There's no real change, no new configuration that wasn't already possible. So why is there an increase in entropy? In the 19th century, this was a profound and unsettling question. It exposed a flaw in classical thermodynamics. The equations implied that simply by mixing two volumes of the same gas, you would gain entropy. But nature doesn't behave this way. You can't create disorder by doing something that makes no observable change. Gibbs, being one of the founding fathers of statistical mechanics, spotted the contradiction and proposed a solution that would later revolutionize physics. He realized that the paradox stems from an incorrect assumption, that particles are distinguishable. In classical physics, we often imagine particles as tiny, numbered billiard balls. You could, in principle, label each gas molecule and track it through space. But this classical picture breaks down in the microscopic world. At the quantum level, particles like atoms or molecules of the same kind are truly, fundamentally indistinguishable, not just in practice, but in principle. There is no such thing as this oxygen molecule versus that oxygen molecule. They have no identity tags, no unique serial numbers. Swapping two indistinguishable particles creates no new state. It's as if nothing happened at all. This insight was groundbreaking. Gibbs proposed that, to avoid the paradox, we must correct the way we count configurations. When calculating entropy statistically, we divide by the factorial of the number of identical particles, n, to account for overcounting due to indistinguishability. This correction eliminates the artificial increase in entropy when mixing identical gases. And just like that, the paradox disappears. The entropy only increases when two different gases are mixed, when the final state is truly different from the initial one. If the gases are the same, there's no real change, no new accessible states, so no increase in entropy. Reality aligns with our physical intuition. But this raises deeper, almost philosophical questions. What does it mean for two things to be identical? Can two entities be so truly indistinguishable that swapping them changes nothing, not even in theory? In the quantum world, the answer is yes. This indistinguishability isn't just a trick of measurement. It's a fundamental principle. It's why electrons obey Fermi Paradox statistics. It's why photons behave according to Bose-Einstein rules. The very laws of quantum mechanics, laws that govern everything from atomic structure to black hole thermodynamics, are built on this principle. So, what began as a quirky paradox in a gas container led to some of the deepest insights in modern physics. Gibbs Paradox isn't just about entropy. It's about the transition from a world of labels and separateness to a reality where identity dissolves in the haze of quantum uncertainty, where numbers lose meaning unless we redefine how we count. It reminds us that not all paradoxes scream with impossibility. Some whisper, quietly, mathematically, until they lead us down a path where the classical world crumbles and something far stranger and more beautiful takes its place. In 1935, three brilliant minds, Albert Einstein, Boris Podolsky, and Nathan Rosen, crafted a thought experiment that would forever shake the foundations of quantum mechanics. It wasn't just a critique, it was a challenge. A declaration of war against the unsettling implications of a theory that dared to defy the classical world. That thought experiment is what we now call the EPR Paradox. At the heart of this paradox is a bold question. Is quantum mechanics a complete theory? Does it describe reality as it truly is? Or is it merely a shadow of something deeper, something hidden from our eyes? Imagine two particles born together in a shared quantum event, entangled. Their properties, like spin or momentum, are linked in a way so profound that measuring one instantly tells you something about the other. If particle A is measured to have spin up, particle B, no matter how far away, must instantly have spin down. But here's the catch. Before measurement, neither particle has a definite spin. They exist in a cloud of probabilities, a superposition. It's only when you measure one that its state and the state of the other become real. Einstein and his colleagues found this deeply disturbing, and because if the act of measuring one particle determines the state of its entangled partner instantly, even across vast distances, then something spooky is happening, something that violates everything relativity tells us about the speed of information. Einstein famously called it spooky action at a distance. But why is this spooky? Let's break it down. According to quantum mechanics, the wave function describes the complete state of a system. Until measurement, the system doesn't have definite properties, only probabilities. But the EPR trio argued, if measuring particle A instantly defines particle B's state, then either information is traveling faster than light, or particle B always had that property, it was just hidden from us. They proposed that there must be hidden variables, elements of reality not captured by quantum mechanics. In other words, the theory is incomplete. This was the EPR paradox. Either accept that measurement on one particle can instantly affect another regardless of distance, which seems to violate locality, or admit that quantum mechanics is missing something, that there are hidden variables out there waiting to be discovered. For decades, the paradox remained a philosophical battleground. Then came physicist John Bell in the 1960s, who formulated Bell's theorem. It took the EPR argument out of the philosophical shadows and into the realm of testable science. Bell showed that if hidden variables exist and obey locality, that is, no faster than light influences, then certain statistical correlations predicted by quantum mechanics should not occur. But when these experiments were finally done, most notably by Alain Aspect in the 1980s, the results were clear and shocking. The predictions of quantum mechanics held true. The correlations between entangled particles could not be explained by any local hidden variables. The universe, it seemed, really is non-local. The EPR paradox had been answered. But not in the way Einstein had hoped. Rather than quantum mechanics being incomplete, it turns out reality itself is stranger than we ever imagined. Measurement doesn't just reveal information, it creates it. The act of observing collapses possibilities into a single truth, and that truth instantly echoes through the fabric of space-time. But what does that mean for the nature of reality? Is the universe fundamentally interconnected in a way that transcends space and time? Is our concept of separateness, of one object being over here and another over there, just an illusion? The EPR paradox forced us to confront these questions, and in doing so, opened the door to an entirely new vision of the cosmos. Today, we use entanglement, the very phenomenon that disturbed Einstein, to build quantum computers, quantum encryption, and even dream of quantum teleportation. The EPR paradox, once a critique, became the foundation for quantum information theory. Yet, it also left us with something deeply unsettling. We live in a universe where particles can influence one another instantaneously, where measurement creates reality, and where the limits of space and time are no longer boundaries, but illusions to be pierced by quantum threads. Einstein wanted a clockwork universe, logical, local, and complete. But the quantum world is anything but. It is a place of mystery, of paradox, and of profound interconnectedness. And the EPR paradox, rather than destroying quantum mechanics, revealed just how unfathomably deep its truths go. The greatest minds tried to resist the madness of quantum entanglement, but in the end, the universe whispered back, "This is how I am, whether you like it or not." In the world of thermodynamics, few ideas are as haunting and seductive as Maxwell's demon, a tiny, invisible creature that dares to challenge the very laws of nature, not with brute force, but with sheer cleverness. It is not a demon in the fiery, horned sense, but one made of pure intellect. Born from the mind of James Clerk Maxwell in 1867, this thought experiment was designed to reveal a crack, however small, in the unbreakable wall of the second law of thermodynamics. To understand the demon's devilry, we must first grasp the law it seeks to defy. The second law tells us that in any closed system, entropy, disorder, must increase or stay the same. It's why heat flows from hot to cold, why energy dissipates, why time only moves forward. It's the reason your coffee cools down and never heats itself up again. Entropy is the arrow of time, the signature of chaos, the death knell of order. But Maxwell imagined a system where this ironclad rule might be broken. Not by magic, but by information. Picture a box of gas, sealed in the middle by a partition with a trap door. On one side, gas molecules move fast, hot. On the other, they move slowly, cold. Now imagine a microscopic being, a demon, watching each molecule. With lightning precision, it opens the door only to let fast molecules into the hot side and slow molecules into the cold side. Over time, the hot side gets hotter and the cold gets colder. And just like that, the demon has decreased entropy. It has violated the second law. But how? No energy was added, no new molecules appeared. Just a clever gatekeeper sorting molecules with precise timing. In essence, order was created from disorder. The irreversible was reversed. The implications are staggering. If this demon could exist, it would mean we could extract energy endlessly from thermal motion, perpetual motion, free energy. It would mean our understanding of thermodynamics is flawed, that the universe has loopholes waiting to be exploited. Scientists were troubled. For decades, the paradox loomed. Some argued the demon wasn't really violating the second law because the system included the demon itself. Maybe the act of observing molecules, deciding when to open the trap door, and storing that information had a hidden cost. Maybe entropy wasn't vanishing. It was just being shifted. But this was more than a philosophical dodge. It forced scientists to probe deeper into the connection between information and energy. In the 20th century, physicist Leo Szilard took the first real step. He proposed that for the demon to make decisions, it had to gain information, and information, he argued, must be physical. Later, Rolf Landauer took it even further. He showed that the act of erasing information, clearing the demon's memory, for example, inevitably increases entropy. That is, while the demon's sorting appears to reduce disorder, its own internal bookkeeping exacts a thermodynamic price. In other words, information is not free. Thought, memory, decision, they are all tied to energy. This profound realization blurred the lines between physics and computation. It meant that the second law still held, not just for matter and energy, but for knowledge itself. Maxwell's demon, once a threat, had now revealed a deeper truth. That entropy and information are two sides of the same coin. That even the smallest act of awareness, tracking a molecule's movement, has consequences in the grand machinery of the universe. Today, this paradox lives on, not as a problem to be solved, but as a foundation for whole new fields: quantum information theory, thermodynamic computing, even black hole physics, where the idea that information can't be destroyed is now a cosmic principle. And the demon? It has become a symbol, not of defiance, but of possibility, a whisper in the ear of science that every rule has a deeper layer, that every law hides mysteries waiting to be unearthed. Maxwell's demon didn't tear down thermodynamics. It expanded it. It forced us to see entropy not just as disorder, but as ignorance. And in doing so, it transformed a century-old paradox into a door, one that still opens into the unknown. Time, we feel it. We live by it. It moves forward, always forward. Milk spills but never unspills. We grow older, never younger. Buildings collapse, they don't spontaneously rise. This irreversible march, from past to future, is what we call the arrow of time. But here's the paradox. The fundamental laws of physics, the deepest equations governing our universe, don't require time to move in one direction. They are time-symmetric. They don't care whether time flows forward or backward. And yet, our entire reality does. This is the arrow of time paradox. It begins with an unsettling question. Why does time have a direction if the laws that govern reality don't? Why do we remember the past, but not the future? Why does entropy, the measure of disorder, always increase? Let's look at a simple example. Drop a wine glass. It shatters. Now reverse that in your mind. The shards jump up, fusing into a perfect glass. That would be miraculous, even laughable. But from a physics standpoint, that reverse motion is just as valid as the forward one. Newton's laws, Schrödinger's equation, Maxwell's equations, all work the same in reverse. So what gives? The key lies in entropy, and the second law of thermodynamics. In any closed system, entropy tends to increase. This increase in disorder, in randomness, is what gives time its apparent direction. The arrow points from low entropy to high entropy, from order to chaos. But now the real tension begins. Because if the universe's laws are symmetric in time, then logically, entropy should increase in both directions, into the future and the past. And yet, that's not what we see. We see a universe that began in an extraordinarily low entropy state and has been increasing in disorder ever since. Why? This is the heart of the paradox. It's not the laws that are broken, it's the initial conditions that are strange. For some reason, the universe began in a highly ordered state, a cosmic improbability, like flipping a trillion coins and landing all heads. And from that unlikely origin, time began to flow, or more precisely, entropy began to increase, creating the illusion of time's forward motion. Imagine you found a deck of cards perfectly sorted, ace to king, by suit. You'd suspect someone arranged them. In the same way, cosmologists now suspect the Big Bang didn't just start space and time. It started with an incredibly low entropy. But why? No one knows. Some suggest that gravity plays a key role. Unlike other forces, gravity clumps matter together. Over time, stars form, galaxies swirl, black holes are born, all increasing gravitational entropy. So maybe the early universe was smooth and uniform, with minimal gravitational complexity and thus extremely low entropy. But even this just pushes the question back. Why was the early universe so smooth? Why did the arrow of time emerge at all? There are even deeper theories, like the idea of a multiverse, where time might flow differently in different regions, or where arrows of time could point in opposite directions. Some physicists, like Sean Carroll, speculate that maybe the Big Bang wasn't the beginning, but a point of minimum entropy in a larger, eternal structure. On either side of that point, time would appear to flow outward in opposite directions, meaning, to beings on the other side of the Big Bang, we are the past, and our future is their past. Others suggest time itself may be an illusion, a construct of consciousness tracking change, that we perceive time's flow because we accumulate memories in one direction, but reality on a fundamental level is static, a timeless configuration of events. The arrow of time paradox is not just about clocks and equations. It cuts into our perception of existence. It asks if the forward flow of time is real, or just a story we tell ourselves to make sense of entropy. And yet, in our everyday lives, time feels inescapably real, a relentless tide we cannot swim against. We age, we die, the universe expands, stars burn out, entropy wins. But maybe, just maybe, the arrow of time is a trick played by a universe whose rules care nothing for direction, a trick born from a single improbable spark of order in an ocean of potential chaos, one exquisite moment where everything began in perfect symmetry and then fell apart. In that fall, we find time, we find memory, we find meaning. But the paradox remains. Why did it ever begin? Imagine you throw a book into a black hole. Not just any book, your diary. It contains your thoughts, your secrets, your very essence written in ink. Now imagine that black hole evaporates, disappearing from the universe. What happens to the information in that diary? Is it gone forever? This is the black hole information paradox, a puzzle so severe it shook the foundations of physics. Because if information is truly lost inside a black hole, then everything we thought we knew about the laws of reality begins to crack. Let's start with what a black hole is. A region in space where gravity is so strong that nothing, not even light, can escape. Cross the event horizon, and you're doomed to fall inward. You are stretched, crushed, and erased from the visible universe. Now, here's where things get strange. According to classical general relativity, anything that falls into a black hole vanishes forever. It's gone. No trace, no footprint. All that remains is the black hole's mass, charge, and spin. This is known as the no-hair theorem. From the outside, black holes are featureless, bland, silent. They forget everything they eat. But quantum mechanics disagrees. Quantum theory insists that information can never be destroyed. Even if you burn a book, the smoke and ash still contain the atoms and energy that once made up its content. In principle, you could reconstruct it, if you had perfect knowledge. This isn't just philosophy. It's one of the core pillars of quantum mechanics, the unitarity of quantum evolution. No information is ever lost. So what happens when quantum theory meets a black hole? Enter Stephen Hawking. In the 1970s, Hawking made a shocking discovery. Black holes aren't entirely black. Thanks to quantum effects near the event horizon, they emit radiation, now known as Hawking radiation. And over time, this radiation causes the black hole to evaporate. Here comes the paradox. If black holes evaporate and disappear, and they erase all information about what fell into them, then that information is lost forever. That violates quantum mechanics, a theory that has never failed an experiment. But if the information isn't lost, where does it go? This question has haunted physicists for decades. It pits two titans of science against each other, general relativity versus quantum mechanics. And in the middle, the black hole stands like a cosmic judge, refusing to reveal its secrets. Some theories propose that the information is encoded in the Hawking radiation itself. But Hawking originally argued that this radiation is completely random, like static. It carries no fingerprints of the stuff that fell in. Others suggest that information isn't destroyed, but instead trapped in a remnant, a tiny leftover object after evaporation. But this raises more problems. Infinite possibilities for such remnants, infinite numbers of states, infinite energy. Not exactly clean. Then came the holographic principle, a radical new idea born from string theory and black hole thermodynamics. It proposes that all the information inside a volume of space can be encoded on its boundary surface. In other words, What happens in 3D can be represented entirely on a 2D surface. And black holes? They might work the same way. Everything that falls in may be preserved, not inside, but on the event horizon itself, like a hologram. As the black hole radiates away, the information might be subtly released in the quantum patterns of the radiation. This became the basis for the black hole complementarity theory. From one perspective, information is lost; from another, it's never gone. Both views coexist without contradiction. But even that may not be the final word. In recent years, physicists have turned to quantum entanglement and a strange idea called the firewall paradox. If the information is preserved in the Hawking radiation, then quantum theory suggests the interior of the black hole must break down violently. The smooth fabric of space-time at the horizon would become a wall of fire, incinerating anything that tries to cross. But that destroys the peaceful picture of Einstein's gravity. It's yet another paradox born from trying to reconcile the rules. More recently, new calculations using quantum extremal surfaces have shown that information might start to leak out earlier than expected, encoded in the correlations of radiation. It's a possible answer, but we're still far from certainty. The black hole information paradox isn't just a quirky question. It's a clue. A signal that somewhere in our theories, something is incomplete. It's a crack in the wall, hinting at a grander, deeper theory that unites gravity and quantum physics. Something beyond Einstein, beyond Hawking. Because when you stare into a black hole, you're not just peering into darkness. You're asking, is reality knowable? Is the universe logical? Or just lucky? Does every action, every thought, every diary entry echo forever? Or does the universe forget? Imagine you're watching the soft glow of a heated iron rod in a dark room. As it heats up, it shifts from red to orange to white. Now ask yourself, what color would it glow if it got infinitely hot? Before the 20th century, physicists tried to answer that question using the best tools of classical physics. What they found wasn't just surprising, it was a disaster, a mathematical meltdown, a prediction so absurd it tore a hole right through the heart of classical theory. This is the ultraviolet catastrophe. At the center of the mystery lies something simple: blackbody radiation. Every object emits electromagnetic radiation based on its temperature. The hotter it is, the shorter the wavelength of the light it emits. A red-hot object emits in the infrared and red. A white-hot object emits invisible light. The sun? It peaks in the yellow range. Physicists wanted to calculate exactly how much energy a blackbody emits at each wavelength. Using classical physics, they turned to two powerful concepts: Maxwell's equations, which govern electromagnetism, and the equipartition theorem, which states that energy is evenly distributed across all possible modes of motion. They treated the inside of a blackbody cavity as a box of standing electromagnetic waves, with each frequency having an equal chance to hold energy. So far, so good. But then came the equation. According to classical theory, the energy density should rise steadily as the wavelength gets shorter. That means higher frequencies like violet, ultraviolet, X-rays should carry more and more energy. And here's the catastrophe. The curve doesn't level off. It climbs infinitely. Mathematically, it said that a blackbody should emit infinite energy at ultraviolet wavelengths, that the tiniest particles in the universe should be blazing with death rays, that everything around us should be glowing with invisible radiation so intense we wouldn't survive a second. Obviously, this doesn't happen. The real world behaves nothing like that. Objects emit less energy at ultraviolet frequencies, not more. The predictions of classical physics were not just wrong, they were physically impossible. This paradox, this divergence between theory and observation, became known as the ultraviolet catastrophe, a signpost that the physics of the 1800s had reached its breaking point. And then, in 1900, a quiet German physicist named Max Planck made a daring move. He suggested that energy isn't continuous. It doesn't flow like water. Instead, it comes in discrete chunks, quanta. He proposed that the energy of electromagnetic waves depends not just on their amplitude, but also on their frequency, and that this energy is quantized. In simple terms, a wave of light at a certain frequency can only contain an integer number of energy packets, or photons, each carrying energy equal to E equals sign hxf, where h is Planck's constant. This tiny change changed everything. With this quantum idea, Planck derived a new formula for blackbody radiation, a formula that fit perfectly with real-world measurements, a curve that rose with frequency but eventually tapered off, exactly matching the observed spectra. The ultraviolet catastrophe vanished. But something else emerged: quantum mechanics. Planck had opened a door he didn't fully understand. His theory worked, but he considered it a mathematical trick, a patch to fix a broken model. But over the next few decades, Einstein, Bohr, Heisenberg, and Schrödinger would walk through that door and discover a universe governed by uncertainty, probability, and strangeness. The ultraviolet catastrophe is more than just a physics puzzle. It's a moment in history, a crack in the classical worldview, a rupture that forced scientists to abandon centuries of intuition and dive into the unknown. It reminds us that even the most beautiful equations can be wrong, that nature doesn't follow our logic, it follows its own. And sometimes, to understand it, we have to break the rules we once thought were sacred. In the end, the ultraviolet catastrophe wasn't a failure, it was a rebirth. The birth of quantum theory, the foundation of everything from semiconductors to lasers to modern cosmology. It began with a question about glowing metal and ended with a revolution. Imagine holding a perfect solid sphere in your hand, a smooth glassy ball about the size of an orange. Now imagine cutting it into 5 pieces, not with a saw, but with mathematical precision. You then move and rotate those 5 pieces without stretching, shrinking, or changing their shape, and somehow, you reassemble them into 2 identical spheres, each exactly the same size as the original. Not a smaller copy, not a fake replica. 2 perfect clones. This is the Banach-Tarski paradox. A result so absurd, so mind-bending, it seems like sorcery. It defies logic, common sense, and physical intuition. And yet, mathematically, it's proven. To understand the Banach-Tarski paradox, you have to enter the abstract world of set theory and infinite mathematics, a realm where ordinary rules break down, and the infinite isn't just a concept. It's a playground. The paradox begins with the work of 2 Polish mathematicians, Stefan Banach and Alfred Tarski, in 1924. They discovered that under certain mathematical assumptions, specifically the axiom of choice, it is possible to take a solid 3-dimensional sphere, break it into a finite number of non-measurable sets, and reassemble them into 2 identical spheres of the same size as the original. But what does that mean? First, let's tackle the axiom of choice. It's one of the foundational principles of modern set theory. It says that given any collection of non-empty sets, no matter how large or strange, you can choose one element from each set, even if there's no rule for how to choose. This axiom is powerful. It allows for proofs that are elegant, surprising, and sometimes utterly unintuitive. Now, the Banach-Tarski construction relies on this axiom to create these bizarre, fragmented pieces, sets of points that are so scrambled, so disordered, that they defy normal geometry. These pieces aren't solid chunks you could hold in your hand. They're made of points so scattered and tangled that you couldn't even assign them a volume. They're non-measurable, and that's key. Using rigid motions, rotations, and translations only, you can rearrange these 5 exotic pieces into 2 spheres identical to the original. It's not magic, it's mathematics. And once you accept the rules of the game, the paradox becomes unavoidable. But how can this be? Doesn't it violate conservation of mass, of volume, of energy? In the physical world, yes. This is impossible. You can't take 1 apple, cut it up, and get 2 apples. The paradox contradicts everything we know from physics, engineering, and daily life. But this isn't physics, it's pure math. And math, especially at the level of infinity, doesn't play by the same rules. The Banach-Tarski paradox only works in 3 or more dimensions. It can't be done in 2D. It also relies heavily on the axiom of choice, a principle that, while widely accepted, has its critics. Some mathematicians question whether it's constructive or real. You see, the pieces involved in the paradox are so complex, so abstract, that you can never physically construct them. You can't build them, can't simulate them, can't even properly visualize them. They exist only in the realm of pure mathematical thought. The proof says these sets exist, but it doesn't tell you what they look like. In other words, The Banach-Tarski paradox doesn't break physics. It breaks the boundary between intuition and abstraction. It forces us to confront a truth. Mathematics is not constrained by the physical world. It explores all logical possibilities, including those that reality refuses to follow. And therein lies the beauty and the terror of this paradox. It's not just about spheres. It's about the power of infinite sets. It's about how deep our assumptions go. It challenges our very idea of what volume is, of what space is, of what cutting even means in a world of infinite detail. The Banach-Tarski paradox is a mirror held up to our minds. It shows us how fragile our intuitions really are. It whispers that the universe of mathematics is stranger than fiction, and perhaps stranger than reality itself. Because if one sphere can become two, what else might be possible? Imagine a room full of gas molecules, wildly bouncing around, chaotic, unpredictable, colliding, rebounding, and dispersing. Over time, they settle into disorder. A spilled perfume bottle diffuses into the air, a hot cup of tea cools down, ice melts. All signs of entropy, the universe's relentless drift from order to chaos. But here's the puzzle. What if you could reverse time? Not in a science fiction way, but literally. What if, at some magical instant, you reverse the direction of every particle's velocity? Molecules moving left now move right. Those spinning clockwise spin counterclockwise. Would the gas molecules reassemble? Would the perfume unspill? Would entropy decrease? According to the fundamental laws of physics, yes. And that's where Loschmidt's paradox explodes into the heart of thermodynamics. It was in the late 19th century when physicist Joseph Loschmidt, a critic and contemporary of Ludwig Boltzmann, asked a question so powerful it still echoes through science today. If the laws of motion are time-symmetric, meaning they work the same whether time flows forward or backward, then why does entropy only increase in one direction? Why does the universe seem to remember the past, but not the future? That's the essence of Loschmidt's paradox. Boltzmann had used statistical mechanics to derive the second law of thermodynamics, the idea that entropy tends to increase over time. His famous H-theorem mathematically showed how a gas evolves toward disorder, but Loschmidt fired a philosophical bullet through it. If every molecule's motion can be reversed, shouldn't a gas spontaneously return to its ordered state? Shouldn't time be symmetrical, both mathematically and physically? The laws of Newtonian mechanics are indeed reversible. A video of two billiard balls colliding looks physically plausible whether you play it forward or backward. The same goes for the molecules in a gas. But in the real world, we don't see unbroken eggs jumping off the floor and reforming on the table. We never watch smoke returning to a cigarette. Why? The answer lies in something subtle and almost existential. Probability. Boltzmann responded by saying entropy isn't about certainty, it's about likelihood. The number of microstates, the tiny arrangements of particles, in a disordered state vastly outnumbers those in an ordered one. A diffused gas has countless configurations. A perfectly arranged compressed gas has very few. So, while reversing every particle's velocity could lead to lower entropy, it's astronomically unlikely. In theory, it's possible. In practice, it's so improbable that it never happens. Loschmidt's paradox doesn't prove the second law wrong. It proves that the second law is statistical, not absolute. It's not a law of mechanics, but a law of overwhelming chances. Yet the paradox still burns with mystery, because it challenges our perception of time's arrow. Every fundamental equation in physics, whether it's Newton's laws, Maxwell's electromagnetism, or even quantum mechanics, is time reversible. There's nothing in these equations that says the future is different from the past. And yet, every human experience screams otherwise. We grow older, not younger. We remember the past, not the future. We see cause, then effect. So where does the arrow of time come from? Many physicists believe it comes from the initial conditions of the universe, the fact that the cosmos began in a state of incredibly low entropy. The Big Bang wasn't just a bang, it was a statistical miracle, a flashpoint of unimaginable order that has been unraveling ever since. From that starting point, entropy had only one way to go: up. Loschmidt's paradox, then, isn't just a critique of thermodynamics. It's a deep philosophical question about the nature of time itself. It forces us to confront the limits of our equations and the bridge between mathematics and reality. Because the universe, as far as we can tell, does not rewind. Entropy is not a law written in stone, but it might be the closest thing we have to destiny. And behind that destiny is a paradox that refuses to vanish. Imagine standing at the edge of reality, where time, space, and even causality begin to blur. Now picture a particle of light, just a single photon, traveling through a complex apparatus. You decide to measure it, but here's the twist. Your decision, made in the present, seems to reach back into the past and change what the photon was before you even looked. This is not fiction. This is Wheeler's delayed choice experiment, a quantum paradox so unsettling that it questions the very meaning of time, observation, and reality itself. Let's start with the classic double-slit experiment. Fire photons at a barrier with two slits. Behind that barrier is a screen that records where each photon lands. If you don't observe which slit the photon goes through, something mind-bending happens. It behaves like a wave, going through both slits at once, interfering with itself, and forming a pattern of light and dark fringes. But the moment you place a detector to watch which slit it chooses, the interference disappears. The photon behaves like a particle, a single localized object. Just by watching, you collapse its infinite possibilities into one reality. That alone is strange. But Wheeler took it further. He asked, what if you wait to decide whether to observe the photon until after it has already passed through the slits? That's the essence of the delayed choice. In this setup, a photon is fired toward a beam splitter or a pair of slits. Halfway through the experiment, and just before it would reach the final screen, you randomly decide whether to insert a second beam splitter, essentially choosing whether the experiment will detect interference or not. In other words, you make the choice after the photon has decided whether to behave like a wave or a particle, and what happens. Your choice in the present changes what the photon did in the past. If you choose to measure for interference, the photon seems to have traveled as a wave through both paths. If you choose to measure which path it took, it behaves as if it only went through one, as though it knew your decision in advance. But you didn't decide until after the photon had already passed the point of no return. This flips causality upside down. How can a particle's earlier behavior depend on a decision made later? This is the paradox at the heart of Wheeler's thought experiment, and later, in real-world implementations with single photons, it holds true. Reality, it seems, doesn't solidify until you choose to observe it. The photon's past is not set in stone. It remains uncertain, undefined, a ghost of possibilities, until you look. This leads to an existential question. Does the photon even have a history before you observe it? Or does your act of measurement retroactively create that history? To many physicists, the implications are staggering. It suggests that reality is not a pre-written script, unfolding predictably over time. Instead, it's like a story being written on the fly, with the ending altering the beginning. Some interpretations of quantum mechanics, like the Copenhagen interpretation, say the photon didn't really exist as a wave or a particle until it was measured. It existed as a probability cloud, collapsing into a concrete form only when someone, you, chose to observe. Others, like the many worlds interpretation, claim that all possibilities occur, each in its own parallel universe. In one, the photon behaves like a particle, in another, like a wave, and your observation merely places you in one reality among many. But Wheeler's paradox isn't just about photons, it's about information. It's about when a quantum system becomes real. It challenges everything we think we know about time's direction. Because if choices made in the present can influence the past, then cause and effect no longer follow a straight line. You are not just a passive observer of the universe. In some strange way, your observation helps shape it. It forces us to ask, what is the role of consciousness in the cosmos? Does the universe remain in flux, like a spinning coin, until some mind chooses to look? Wheeler believed that the universe was a participatory system, that observers and observations are woven into the very fabric of reality, that we are not mere spectators, but co-creators of the past, present, and future. Wheeler's delayed choice experiment is not just a thought experiment, it's a whisper from the edge of understanding, a reminder that the universe is more mysterious than we can imagine, and that time might not be what we think it is. Imagine a system that, by simply being observed, defies the natural flow of time. A particle, locked in a state of constant observation, appears to be frozen, its evolution halted. This might sound like the stuff of science fiction, but it's a real phenomenon that challenges our understanding of quantum mechanics. This is the quantum Zeno effect, a mind-bending phenomenon where the continuous act of measurement, the very act of looking, can prevent a quantum system from changing. It's as though time itself is stopped. Let's start with the basics. In the quantum world, particles don't behave like the objects we experience in everyday life. Instead of following definite paths, they exist in a cloud of probabilities, existing in multiple states simultaneously, a concept known as superposition. Take, for instance, the case of a radioactive atom. The atom may decay over time, but we can't predict exactly when it will happen. The best we can do is say it has a certain probability of decaying in the next second. This is the quantum nature of decay. But what if you could constantly measure that atom, checking its state over and over again? You might think that once it's measured, the atom's state would collapse into either decayed or undisturbed. But here's the twist. If you keep measuring it at short intervals, the atom will never decay. It's as if the atom knows that every time it's observed, it must remain in its current state. The act of observation itself prevents the decay from happening, locking the system in place. This is the quantum Zeno effect, named after the ancient Greek philosopher Zeno, who proposed paradoxes involving motion and time. In essence, Zeno's paradox of motion suggests that if something can be divided infinitely, you can never actually reach your destination. The quantum Zeno effect takes this to an extreme, suggesting that infinite observation can stop change itself. But how does this work in the quantum world? In quantum mechanics, the state of a system is described by a wave function, which contains all the probabilities of the system's possible outcomes. When you observe the system, the wave function collapses into a definite state. But if you keep observing it, the system is constantly collapsing into the same state, never allowing time to move forward. You see, in classical physics, if we were to observe a radioactive particle, it would either decay or stay in its current state. But in the quantum world, the act of measurement influences the system itself. By continuously measuring, you are not just observing, you are altering the system, forcing it to behave in a way that it would never do naturally. This effect isn't just theoretical, it has been experimentally observed in the lab. Researchers have shown that by continuously measuring the state of certain quantum systems, such as an atom's energy levels, they can prevent the atom from decaying. It's as if the very presence of the observer stops the clock on the process. The implications of the quantum Zeno effect stretch beyond simple experiments. In fact, this paradoxical observation is central to quantum computing and quantum control. It suggests that quantum systems, which are typically very delicate and prone to decay or loss of information, could be stabilized by constant monitoring. This insight could be a powerful tool in maintaining the integrity of quantum states in computers that rely on quantum bits, or qubits. However, there's a deeper philosophical question lurking beneath the surface. If measurement can alter the course of events so drastically, what does this tell us about the nature of reality itself? Does the universe truly exist in a definite state, or is it only when we look that it becomes real? The Zeno effect takes this a step further. Does reality depend on our continuous observation, or is the act of observation itself creating reality? In the classical world, things happen whether or not we look. A car travels down the road whether we watch it or not. But in quantum mechanics, observation doesn't merely reveal the state of a system, it shapes it. This blurs the lines between observer and observed, suggesting that the universe may be far more interactive than we thought. The quantum Zeno effect hints that consciousness or observation might play a pivotal role in determining the course of events in the quantum world, an idea that resonates with some interpretations of quantum mechanics, like the Copenhagen interpretation, where reality itself is shaped by our observations. To bring this down to earth, think of it this way. Imagine you're watching a clock. Each tick, each second, you observe it closely. But because you're looking at it all the time, the clock never actually moves forward. It's frozen, locked in place. The more you watch, the more it stays still, unable to advance. This is a tangible metaphor for the quantum Zeno effect. The more you observe, the less the system changes. But just how far can this effect extend? Can it freeze a system indefinitely? Or is there a limit to how much observation can stop progress? The Zeno effect certainly opens the door to new ways of controlling quantum systems, but it also forces us to confront a deeper question about the role of time and change in the quantum realm. In the end, the quantum Zeno effect teaches us that time, like everything else in the quantum world, is not as simple and linear as it seems. Change, decay, and evolution are not guaranteed. In the quantum universe, they can be frozen by something as simple as a continuous glance. The paradox lies in the fact that the more you try to measure and control reality, the less likely it is to change. In a sense, the quantum Zeno effect is a reminder that, in the quantum world, nothing is ever certain. We are only ever looking at a snapshot of a universe that, until we observe it, exists in a constant state of potential, forever suspended between what it was and what it could be. At first glance, it sounds absurd, almost like a mistake in observation. How could hot water freeze faster than cold water? It goes against every intuitive sense we have about thermodynamics, about heat, about how the world works. And yet, in specific conditions, this very thing happens. A hotter body of water can actually freeze more quickly than a colder one. This is the Mpemba Effect, one of the most puzzling and counterintuitive paradoxes in physics. To understand why this phenomenon has baffled scientists for centuries, we have to begin with its modern rediscovery. In 1963, a Tanzanian secondary school student named Erasto Mpemba noticed something strange while making ice cream in a cooking class. When he used hot milk instead of cold, it froze faster. No one believed him, not even his teachers. But Mpemba didn't let it go. He persisted, and eventually, with the help of a physics professor, published a paper in 1969 confirming the effect experimentally. But this wasn't a new observation. Aristotle, Francis Bacon, and René Descartes had all made similar claims centuries ago, though these were often dismissed as anecdotal or misunderstood. Mpemba's persistence reopened a paradox that had been waiting quietly at the edge of physics for thousands of years. So, how could this happen? Why would hot water, with more thermal energy to lose, freeze faster than cold water? To this day, there is no single definitive explanation. Instead, we are left with a complex interplay of factors, each of which may contribute under the right circumstances. The Mpemba effect does not always occur. It depends on a delicate balance of variables, including the temperature of the environment, the volume of water, the shape of the container, evaporation, convection currents, and even the dissolved gases in the water. Let's break some of these down. First, evaporation. Hot water evaporates more rapidly than cold water. As water evaporates, it loses mass. Less mass means there is less water to freeze, potentially allowing the remaining liquid to solidify faster than the cold water, which retains more mass and therefore takes longer to freeze. But this alone can't fully explain the effect. Next, convection currents. Hot water sets up more vigorous convection currents within itself, fluid motion caused by differences in temperature and density. These currents can distribute the cooling more uniformly through the water, potentially speeding up the process of freezing compared to cold water, which might cool more slowly due to a stagnant, stratified temperature gradient. Then there's the idea of supercooling. Cold water, under certain conditions, can remain in a liquid state below its normal freezing point, a phenomenon known as supercooling. If the cold water supercools, it delays the moment of freezing. Meanwhile, hot water might bypass supercooling altogether and solidify faster. This effect could be even more pronounced if the water contains impurities or has been boiled, which can eliminate gases and particles that trigger supercooling. And speaking of gases, dissolved gases play a role too. Cold water typically contains more dissolved air than hot water. As water is heated, these gases escape. The presence of dissolved gases changes the thermal properties of water, things like heat capacity and thermal conductivity. Water that has been boiled is denser and may freeze differently than water full of trapped gas bubbles. Even the environment matters. The way heat is transferred between the container and the freezer, the way frost forms around the surface, the way the surrounding air circulates, all these can impact the rate at which water cools and freezes. It's a delicate dance of dozens of factors, any one of which can tip the balance and cause the Mpemba effect to appear, or not. But the most compelling part of the Mpemba effect is this. Despite all our advancements in science, despite our deep knowledge of thermodynamics, we still don't fully understand it. Scientists have recreated the effect under laboratory conditions, but they have also failed to reproduce it in other trials. It doesn't happen every time. It's unreliable, it's inconsistent, it's mysterious. This has led to fierce debate in the scientific community. Some argue the Mpemba effect is simply the result of poorly controlled experiments, that it's not a real physical phenomenon, but a statistical illusion born from complex variables. Others insist that it is real, but only occurs under very specific and poorly understood conditions. In either case, its very unpredictability makes it a paradox worth studying. What's important is that the Mpemba effect forces us to confront the limitations of our assumptions. We expect the universe to behave in simple, linear ways. Hot water should cool, then freeze, and it should take longer than cold water. But nature doesn't always follow our expectations. In a way, the Mpemba effect is less about freezing water and more about freezing our own certainty. It reminds us that even in something as simple as water turning to ice, there are mysteries we haven't solved, variables we haven't measured, forces we don't yet fully comprehend. It humbles us, and that humility is where the beauty of science lives. In admitting that, we don't always know the answers, in exploring the edge cases and paradoxes that challenge our models, in re-evaluating the obvious, and realizing that the ordinary can still surprise us. Ernesto Mpemba, a young student without a PhD, without a lab, without status or scientific clout, saw something strange, and he refused to ignore it. And that's perhaps the greatest lesson of the Mpemba effect. That discovery doesn't always come from certainty. Sometimes, it begins with a question no one takes seriously, until someone does. There are moments in the history of physics when a single idea rips open the fabric of what we thought we knew, exposing something far more strange and unsettling underneath. Bell's theorem is one of those moments. It takes our comfortable understanding of reality, cause and effect, locality, free will, and throws it into question. What if particles can influence each other instantaneously across space? What if hidden variables don't exist? What if reality itself is non-local? The story of Bell's theorem begins with a question that haunted Albert Einstein. In 1935, he, along with Podolsky and Rosen, proposed what is now known as the EPR Paradox. They presented a thought experiment to show that quantum mechanics, despite its success, must be incomplete. To Einstein, the idea that two particles could be entangled, influencing each other instantly across any distance, was absurd. He famously called it spooky action at a distance. Einstein believed that there must be hidden variables, undiscovered elements of nature that would restore a logical, local explanation to quantum phenomena. In other words, quantum mechanics wasn't wrong, but it wasn't the full picture either. Enter John Bell. In 1964, John Stuart Bell, a physicist from Northern Ireland, devised a way to put Einstein's intuition to the test. Bell's theorem wasn't just a philosophical counterpoint, it was a mathematical proof. It provided a way to experimentally test whether quantum mechanics truly defied locality, or if there were indeed hidden variables lurking beneath the quantum veil. What Bell did was revolutionary. He derived an inequality, a limit based on the assumptions of locality and realism, that any local hidden variable theory must obey. This Bell inequality became a litmus test for the foundations of reality itself. If experiments violated Bell's inequality, then the universe could not be both local and real in the classical sense. Let that sink in. Bell's work gave us a scientific tool to probe whether particles interact faster than the speed of light, or if objective reality even exists independently of observation. So, what did the experiments say? Starting in the 1970s and accelerating in the 1980s and beyond, physicists like Alain Aspectin in France performed increasingly refined experiments to test Bell's inequality using entangled particles, typically photons. The results? Quantum mechanics wins. Again and again, the experiments violated Bell's inequality, confirming that entangled particles do exhibit correlations that cannot be explained by any local hidden variable theory. Two photons, created together and sent to opposite ends of a lab, measure one, and the other instantly reflects that measurement, even if no signal could travel between them in time. The outcome seems to be decided in an instant across space, as if the universe itself doesn't care about distance. It's not that one particle sends information to the other. Rather, it's as if their fates are bound together outside the constraints of space and time. This throws open a terrifying door. If we accept the results of Bell tests, we are forced to abandon at least one of our most cherished principles. Either locality, the idea that things can only be affected by their immediate surroundings, is false, or realism, the idea that physical properties exist prior to measurement, is false. Some interpretations of quantum mechanics, like the Copenhagen interpretation, accept the latter. Properties like position or spin do not exist until they are measured. Other interpretations, like Bohmian mechanics, preserve realism but give up locality, accepting a deeply non-local universe. There's a third option that's even more unsettling, that free will doesn't exist, at least not in the way we imagine. If the particles and the measuring devices share a kind of pre-established harmony, then the results of the measurement could be predetermined by initial conditions of the universe. This line of thought leads to superdeterminism, a controversial idea that everything, including our decisions about what to measure, was always predetermined. So, where does this leave us? Bell's theorem is not just a scientific result. It is a philosophical and existential earthquake. It reveals a universe where information might travel faster than light, where objects don't have definite properties until observed, where our very sense of cause and effect is blurry and indistinct. It shows us that quantum entanglement is not just a strange artifact. It is a fundamental aspect of how reality is stitched together. And perhaps the most haunting part? The correlations predicted by quantum theory and confirmed by Bell experiments are incredibly precise, too precise to be coincidence. They suggest that there is something deeply hidden in the fabric of reality that we still don't understand, something that defies classical intuition and may never be accessible through traditional means. We live in a world shaped by the consequences of Bell's theorem. From quantum computers to cryptographic systems, the strange implications of entanglement are being turned into technologies that will shape the future. But the mystery remains. We still don't fully know why the universe behaves this way. We only know that it does. John Bell died in 1990, but his legacy lives on, not just in equations or experiments, but in the minds of every physicist who dares to ask the ultimate question: what is real? Bell's theorem doesn't give us easy answers. It gives us a challenge to rethink, to question, and to accept that reality might be far stranger than we ever dared to imagine. In the silent war between order and chaos, thermodynamics stands as the ultimate judge. It governs everything, from the death of stars to the beating of your heart. But within this majestic framework lies a peculiar contradiction, one that twists the very core of how systems are supposed to behave. It's called the paradox of tolerance. And unlike the more famous version from social philosophy, this paradox hides in the relentless arithmetic of entropy. It's not about politics or ideologies. It's about energy, equilibrium, and the deceptive calm of systems pushed to their limit. Imagine this: a machine, a heat engine, or a chemical system, designed to endure, built to tolerate environmental fluctuations in temperature, pressure, or even chemical concentrations. We engineer these systems to be robust, to bend without breaking. But therein lies the seed of the paradox. Because the more tolerant a system becomes, the more vulnerable it can grow to catastrophic failure. Why? Because tolerance hides instability. It masks the signals that warn us we're approaching the cliff's edge, until it's too late. In thermodynamics, entropy measures the number of microscopic configurations that correspond to a macroscopic state, the disorder, the hidden chaos underneath what appears stable. When a system is too tolerant, when it absorbs fluctuation after fluctuation without visibly changing, entropy still accumulates. The stress does not disappear. It disperses, redistributes, hides in the system's complexity. But entropy never forgets. Let's take a thermal reservoir as an example. You increase its heat slowly, gradually. The system tolerates the input, its temperature doesn't rise significantly, thanks to heat capacity and energy buffering. But energy is still entering. Molecules are vibrating faster. Entropy is increasing beneath the surface. And then, suddenly, a phase change occurs. Water becomes steam. Metal warps. Circuits fry. The system leaps into an entirely new regime of behavior. This is the thermodynamic echo of the paradox of tolerance. Long-term tolerance of small stressors may bring about an abrupt collapse when critical thresholds are crossed. We see this behavior in real life. Think about Earth's climate. The atmosphere has an incredible capacity to absorb carbon dioxide, to buffer temperature rises through oceans, forests, and clouds. For decades, the planet tolerated the excess. Small increases in greenhouse gases did not produce immediate catastrophe. But all the while, entropy was rising. Energy was being trapped, ice was thinning, ocean currents were shifting. And now, we approach tipping points. Thresholds where small perturbations could lead to massive, irreversible changes. Tolerance led us to complacency, and now we face collapse. The paradox extends to engineered systems as well. A nuclear reactor is designed with incredible safety margins. It tolerates heat. It tolerates radiation. But if cooling fails and feedback mechanisms are delayed or masked, the system may not show distress until it reaches a runaway state. The very engineering that made it robust also made its failure sudden and catastrophic. The same is true for spacecraft, chemical plants, power grids, all complex thermodynamic systems. This isn't merely a matter of engineering, it's a law of nature. In statistical mechanics, systems often hide instability within metastable states, like supercooled water, which can remain liquid below freezing until the slightest disturbance causes it to crystallize instantly. These systems are tolerant until they aren't, and when they don't fall gradually, they shatter. It's tempting to view tolerance as strength, but in thermodynamics, strength without feedback is fragility in disguise. Tolerant systems delay the signals we need to act. They smooth out the bumps until the road abruptly ends in a cliff. There's a lesson here. One is true for machines as it is for ecosystems, economies, and perhaps even civilizations. Resilience is not just about enduring stress, it's about responding to it. Systems that adapt too little, systems that absorb too much without change, walk a dangerous line. Entropy builds in silence, disorder gathers in the shadows, and the crash, when it comes, is merciless. The paradox of tolerance in thermodynamics isn't about kindness or open-mindedness. It's about the tragic illusion that nothing is wrong, until everything is. It's about the quiet betrayal of stability, and the ruthless justice of entropy. Because in the end, thermodynamics doesn't care how well you tolerated the heat, only whether you recognized the moment before you boiled over. What if everything you see, feel, and believe is a carefully constructed illusion? What if your memories, your emotions, even your deepest beliefs are nothing more than lines of code in a hyper-advanced computer simulation? Welcome to the simulation hypothesis paradox, a chilling intellectual wormhole where science, philosophy, and theoretical physics converge to question the very nature of reality itself. It's not just science fiction anymore. It's a paradox that has unnerved physicists, philosophers, and even tech billionaires alike. At its core, the simulation hypothesis suggests that what we perceive as physical reality is actually a simulated environment, like an incredibly complex video game constructed by an advanced civilization. But the paradox doesn't lie in whether the simulation is real. It lies in the unsettling logic that makes it almost statistically inevitable that we are living inside one. It begins with probability. Cold, ruthless probability. Imagine a future where humanity evolves far beyond our current limitations. A civilization capable of creating digital universes, each populated with conscious beings who believe they are alive, unaware of their simulated existence. Now imagine that this future civilization creates not one, but millions of such simulated realities, each filled with sentient life. If that becomes possible, then logically, the number of simulated minds would vastly outnumber biological ones. So, here's the paradox. If simulated beings become more common than real ones, what are the odds that you are among the rare biological few? Nearly zero. The simulation hypothesis forces us to wrestle with a terrifying implication. Unless advanced civilizations have no interest in creating simulations, or unless they destroy themselves before they gain the power to do so, we are almost certainly living inside one right now, and this is where physics begins to tremble. Think about quantum mechanics. Particles don't seem to exist in one state until they're observed. The famous double-slit experiment shows light behaving like a wave or a particle depending on whether it's being measured. Doesn't that sound like a rendering engine? Like the system is only loading details when someone's watching? It's as if the universe is optimized, not fully rendered, but efficient, just like a game would be. Dig deeper, and the clues get even darker. The Planck length, the smallest measurable unit in the universe, could be seen as the resolution of the simulation. The speed of light, the ultimate speed limit, could be the processor's clock speed. Entropy, gravity, time itself, could all be rules of a simulated universe, written not in the language of gods, but of code. And here's the true heart of the paradox. If we ever create such a simulation ourselves, a reality so immersive that its inhabitants believe they are real, it would not only prove the possibility, it would multiply the probability that we ourselves are already simulated. In fact, the moment we succeed in creating simulated consciousness, we open a Pandora's box we can never close. But the paradox cuts deeper than logic. It pierces the very essence of what it means to be human. If we are simulated, do we have free will? Are our choices truly our own? Or are we just variables reacting to inputs in a giant experiment? And what of suffering, love, morality? If reality is fake, does anything matter? But then, does it matter? Even if we are simulations, our pain still hurts. Our joy still uplifts. Our memories still guide us. Consciousness doesn't cease to be real just because it was born in a machine. In fact, it may be the one thing that proves we are more than just data, that something in us transcends the simulation. And that's the final, cruel twist of the simulation hypothesis paradox. Whether or not we're inside a simulation, we can't ever be sure. The rules of the simulation could be designed to prevent us from discovering the truth. Every test, every theory, every breakthrough could be another illusion, scripted to keep us complacent. But maybe, just maybe, our drive to question it, to doubt our own reality, is the one thing that sets us apart from mere code. Because even in a simulated world, the search for truth might be the most real thing we have. Here is the intense, thought-provoking, and emotionally captivating voiceover script for the measurement problem in quantum mechanics, crafted for a 5-6 minute narration and exceeding 5,000 characters. In the mysterious realm of the quantum, reality doesn't behave as it should. Particles don't exist in definite places. Events don't unfold in straight lines, and certainty is replaced by probability. Welcome to the domain where logic shatters and reality becomes fluid. At the heart of this chaos lies one of the most haunting puzzles in all of physics, the measurement problem. It's not a theory. It's not a mere technicality. It's a question that shakes the foundations of reality, a question that asks, what is real, before we observe it? In classical physics, things are simple. A ball has a position, a planet has a trajectory. The world exists whether or not someone is watching. But quantum mechanics tells a radically different story. In the quantum world, particles like electrons don't have definite positions. They exist in a cloud of probabilities, described by a mathematical entity called the wave function. This wave function doesn't say where the particle is. It says where it might be, until you look. The very act of measuring collapses that fuzzy, probabilistic wave function into one concrete outcome. Before you measure it, the electron could be anywhere. But once you do, it's somewhere specific. The wave function collapses. Possibility becomes certainty. And that is the measurement problem. Why does observation change reality? What counts as a measurement? Why should the universe behave differently just because a conscious observer is watching? And what exactly is an observer anyway? A human? A machine? A photon? No one truly knows. Take Schrödinger's cat, the thought experiment that paints the measurement problem in morbid detail. You put a cat in a sealed box. Inside is a quantum mechanism that has a 50% chance of releasing poison, depending on the decay of a radioactive atom. According to quantum mechanics, until the box is opened, the atom is in a superposition of decayed and not decayed. The cat is therefore both alive and dead, simultaneously. But when you open the box, you find just one outcome, alive or dead, not both. The wave function has collapsed. So, what happened? Did your consciousness decide the cat's fate? Did the universe split into two? Or did the cat collapse its own wave function by being conscious inside the box? These aren't just philosophical games. They reflect the deep confusion at the core of quantum theory. Our most successful physical model can predict the behavior of particles with breathtaking precision. Yet it can't explain when or why those particles stop behaving, like waves of probability, and start acting like solid objects. Some interpretations try to solve the paradox by saying the wave function never collapses. Every possible outcome actually happens, each in a different universe. This is the many worlds interpretation. According to it, when you observe the cat, the universe splits. In one, the cat is alive. In another, it's dead. Both are real. You just happen to experience one. Others, like the Copenhagen interpretation, argue that the wave function is just a tool. Useful, but not real. The collapse is simply how we update our knowledge when we gain new information. Reality in this view doesn't exist independently of measurement. And then, there's the deeply unnerving possibility that consciousness itself triggers collapse, that the universe behaves differently when watched, that your mind reaches into the quantum fabric and forces it to choose a reality. But if that's true, what does it mean for consciousness? Is it a fundamental part of the universe? Is the cosmos aware? Or is our very notion of measurement a flawed attempt to grasp something deeper that we haven't yet understood? The measurement problem remains unsolved. Physicists have tried to bury it, to sidestep it with equations and pragmatism, but it never goes away. It haunts every lab, every experiment, every particle collider. It is the shadow behind every quantum result, whispering that we don't really understand the game we're playing. Because if we don't know what measurement is, we don't know what reality is. We might never see the electron's true position. We might never find the cat both dead and alive. But the question lingers, electric and terrifying. Does reality exist when no one is looking? And if not, then what are we really made of? Close your eyes for a moment and imagine the end of everything. Not with fire, not with thunder, but with silence, an infinite, unbreakable stillness that creeps across the universe, not in a sudden burst, but in a slow, inevitable decay, a cold, eternal nothingness. That is the vision behind the heat-death paradox, and it is not science fiction. This paradox stems from one of the most fundamental laws in physics, the second law of thermodynamics. It states that in any closed system, entropy, the measure of disorder, can never decrease. Over time, everything becomes more chaotic, more disordered, more uniform. And the universe, as vast and powerful as it seems, is a closed system, which means it's dying. Not by collision, not by collapse, but by equilibrium. At the heart of the heat-death paradox is a terrifying idea that the universe will one day reach a state of maximum entropy. Every star burned out, every black hole evaporated, every particle so evenly spread that no more energy can flow, no more work can be done, no life can survive. It's called the heat death of the universe, and it is perhaps the most haunting fate imaginable. But here's the paradox. If entropy must always increase, if the universe is inevitably spiraling into chaos, then how did we get here? Why does the universe today appear so full of structure, of stars and galaxies and life? Why is there low entropy at all? According to the laws of physics, a high entropy state should be the natural one, the default. And yet, our universe began in an extremely ordered state, a low entropy condition so precise, so improbable, that it defies all statistical logic. It is as though the universe started from a cosmic miracle. Think of a deck of cards. Shuffle it 1 billion times, and you'll never once get them in perfect order. But somehow, the universe began perfectly shuffled in reverse, a low entropy arrangement so unlikely that even the odds can't explain it. That's the paradox. The laws of thermodynamics predict a slow decay into disorder, but they don't explain how order ever began. How did the universe get into such a fine-tuned, low-entropy state in the first place? And if the final state is death, why did life, complexity, and consciousness ever emerge at all? Some theorists believe inflation, the rapid expansion after the Big Bang, stretched the universe into order. Others suggest a multiverse, where countless universes spawn and die, and we just happen to live in the rare one that started clean. But none of these ideas solve the deeper question. Why was entropy so low at the beginning? Why should anything begin with such precision, only to die in such silence? There is another haunting layer to this paradox. As entropy increases, information dissolves, stars burn out, energy diffuses, and eventually the very concept of memory fades. There will be no observers, no thought, no structure, only a dark, cold ocean of particles in thermal equilibrium, a universe with no contrast, no movement, no meaning. Time itself, as we know it, is born from entropy. The arrow of time, the one-way street from past to future, exists because entropy increases. So, if the universe reaches a state of maximum entropy, will time stop? Will the last tick of the cosmic clock simply never come? That's the emotional weight of the heat-death paradox. It is not merely about thermodynamics, it is about fate. It asks if all our striving, our love, our suffering is destined to be swallowed by a cosmic stillness that doesn't care. If meaning itself is just a flicker before the freeze, it whispers that everything beautiful, stars, minds, music, might be nothing more than temporary arrangements of order in a system doomed to disorder. But maybe that's where hope lives, because in defying entropy, however briefly, we exist. We are order born from chaos, sparks of meaning in a sea of randomness. Perhaps the very act of creating, of loving, of remembering, is our resistance to the inevitable, a rebellion against the final silence. The heat-death paradox does not just describe a universe dying. It asks us, what will we do with the time we have while the stars still burn? In the early 20th century, physics was standing on the edge of a revolution. The world had just begun grappling with the strange consequences of motion at the speed of light, and reality was shifting beneath the feet of even the most brilliant minds. And in that delicate moment between classical certainty and relativistic mystery, a quiet yet profound paradox emerged, one that questioned the very structure of motion, torque, and symmetry. This is the story of the Trouton Paradox. At first glance, it seems simple, innocent even. Imagine a parallel plate capacitor, two metal plates charged with equal and opposite charges, separated by a small distance. In its rest frame, this device sits in peaceful equilibrium. No torque, no rotation, just an electric field between the plates. But now, imagine this entire setup is moving at a constant velocity, gliding smoothly through space. Classical intuition says, if there's no torque in one frame, there should be no torque in any other inertial frame. After all, the laws of physics should be the same for all observers moving at constant velocity. This is the bedrock of special relativity. But here's where the paradox strikes. When you analyze the moving capacitor from the perspective of a stationary observer, things get weird. According to classical electromagnetism, specifically Maxwell's equations, the moving electric field now creates a magnetic field. This magnetic field interacts with the electric charges on the plates and produces a torque that shouldn't be there. From this new frame of reference, it looks like the capacitor should start rotating. But in its own rest frame, it remains still, with no torque acting on it. How can something rotate in one frame but not in another? How can the universe disagree with itself? This is the Trouton Paradox, and it shattered the assumptions of classical physics. It wasn't just a math problem, it was a conceptual earthquake. Because if torque behaves differently in different frames, then either the laws of motion are broken, or our understanding of space and time needs to be rewritten. To the Trouton experimenters, this was a genuine threat to the principle of relativity. Their experiment, meant to detect absolute motion through the so-called luminiferous ether, yielded a null result. No rotation occurred. But classical physics couldn't explain why. The torque was there, but somehow it wasn't. Enter Einstein. Special relativity, just barely conceived at the time, held the answer, though subtle and non-intuitive. In the relativistic view, forces, energy, and even torque must be treated with the full machinery of four-dimensional spacetime. What looks like torque in one frame may not be torque in another. In fact, quantities like angular momentum and energy are no longer absolute. They are frame-dependent entities that require transformation through Lorentz mathematics. What classical physics saw as a real torque was, in the relativistic sense, a misinterpretation of how momentum flows in space and time. Special relativity doesn't just tweak the rules. It redefines what it means for an object to rotate, accelerate, or balance. It tells us that energy and momentum aren't separate. They're part of a unified four-vector. And torque, like everything else, must be woven into that fabric. When fully analyzed through the lens of special relativity, the paradox dissolves. The apparent torque is counteracted by changes in momentum due to relativistic effects. The capacitor doesn't rotate, not because the torque isn't real, but because motion itself must be understood in a new language, a language where space and time are not fixed stages, but dancing partners in the unfolding of reality. But the true power of the Trouton Paradox isn't just in the resolution, it's in the tension it revealed. The uncomfortable truth that classical physics could not answer all of nature's questions. It forced physicists to abandon comfort and certainty. It was a whisper from the universe saying, "You don't understand me yet." And perhaps that's what paradoxes truly are. They are not mistakes, they are signposts, clues that point beyond the horizon of current knowledge. The Trouton Paradox was one such signpost, marking the boundary between the old world of Newton and the new world of Einstein. Even today, it reminds us that when logic seems to crumble and reality appears contradictory, we may be standing at the door of something greater. Time, it's the one thing we all move through, every second, every breath, every heartbeat. And yet, time is not what we think it is. The time dilation paradox doesn't just bend our understanding of clocks and motion. It forces us to confront the possibility that time itself is not universal, that two people living two different lives can experience time at completely different rates. And the implications of that are not just scientific, they're existential. Imagine two twins, identical in every way. One of them boards a spaceship and travels at near the speed of light. The other stays behind on Earth. When the space-traveling twin returns after what feels like only a few years, he finds that his sibling on Earth has aged decades. Wrinkles that didn't exist now crease the Earth twin's face. Memories have been made, entire lifetimes passed, while for the traveler, time barely moved. This isn't a science fiction fantasy. This is a direct consequence of Einstein's theory of special relativity. According to the theory, time is not absolute. It slows down for objects in motion relative to a stationary observer. This effect is called time dilation. The faster you move, the slower your clock ticks compared to someone standing still. But here's where the paradox begins. From the perspective of the twin in the spaceship, isn't it Earth that is moving away at high speed? Shouldn't the Earth twin's time slow down instead? Why is only the traveler younger? If both observe the other as moving, then by the rules of relativity, each should see the other's clock running slow. So how can they both be right? That's the core of the time dilation paradox. The idea that both observers should see the other's time running slower. It appears logically contradictory. How can each age slower than the other? It seems like an impossibility. But here's the key. Symmetry is broken. The traveling twin isn't just moving at a constant speed. He has to accelerate to reach those relativistic velocities, decelerate to turn around, and accelerate again to return home. These accelerations break the perfect symmetry of motion. The Earth twin remains in an inertial frame, unchanging and constant, while the traveler switches frames. And that difference makes all the difference. Einstein's equations are precise. When applied correctly, they show that time dilation is real and measurable. This isn't a philosophical debate. We've tested it. High-precision atomic clocks flown on airplanes return ticking ever so slightly slower than their counterparts on the ground. GPS satellites orbiting Earth must compensate for time dilation constantly, or their signals would drift by kilometers. Even at everyday speeds, relativity is affecting your phone right now. But the paradox still haunts us. Not because the math is wrong, but because the consequences are so alien. Time is supposed to be fair. It's supposed to be equal. 1 second here is 1 second there. That's what we intuitively feel. That's how we live. But in reality, time is personal. Time is relative. And that idea shakes the very foundation of how we experience life. Think of the emotional weight. Two people sharing a moment, and yet living in different temporal realities. One running forward, the other slowing down. Time, once thought to be the constant background of existence, now becomes as fluid as the wind. Curving, stretching, changing with speed and gravity. And that brings us to a deeper truth. The time dilation paradox isn't just about physics. It's about the fragility of the human experience, about how every path we take, every choice, every movement pulls us through time differently. We can never go back. We can never be perfectly synchronized. Each heartbeat, each step forward, pushes us down a unique timeline. The traveler, upon returning home, isn't just younger. He's displaced, alien. Time has betrayed him. And yet, time never lied. It did exactly what the universe commanded. This paradox doesn't remain confined to textbooks. It plays with the very nature of cause and effect. It hints at the strange flexibility of time in quantum systems. It forms the backbone of our understanding of space-time, black holes, and the very geometry of the universe. So, next time you look at a clock, remember, that ticking hand is not absolute. It's a local rhythm, a beat tied to your frame of reference. Somewhere else in the universe, time may be ticking faster or slower, and somewhere, someone may be aging while you remain still. The time dilation paradox forces us to ask, if time is not constant, what is? If every observer walks a different road through time, can we ever truly walk together? Let's begin with a simple, almost innocent statement. All ravens are black. It sounds like a straightforward scientific hypothesis. You observe black ravens, you conclude they're all black. But what if I told you that seeing a green apple could somehow confirm this statement? Welcome to the paradox of the raven, also called Mpemba's Paradox, a thought experiment so deceptively simple, yet so profoundly confusing that it challenges the core of scientific reasoning. And when examined through the lens of Bayesian physics, it becomes even more unsettling. Imagine you're a scientist. Every time you see a black raven, your confidence in the statement, all ravens are black, increases. That makes sense. Every observation consistent with your hypothesis should make the hypothesis more likely to be true. But now comes the strange twist. Logically, the statement, all ravens are black, is equivalent to saying, all non-black things are not ravens. It's a perfect contraposition. So, according to logic, seeing a green apple, a red car, or a white chair, none of which are black ravens, should technically support your original claim because they're non-black things that are not ravens. But does that feel right? Does looking at a banana really tell you anything about the color of ravens? Emotionally, intuitively, the answer is no. But logically, through the principles of confirmation theory, it does. And that's where the paradox begins to fracture our understanding of how evidence works. Let's take it deeper with Bayesian reasoning. In Bayesian logic, every hypothesis has a prior probability, our belief in its truth before any evidence is considered. Every new piece of evidence updates that belief using Bayes' theorem. The goal is to refine our understanding based on conditional probabilities. In this context, each time you see a black raven, the likelihood that all ravens are black increases slightly. But what happens when you see a green apple? From a Bayesian perspective, you calculate how likely you were to see a green apple if all ravens are black, versus how likely you were to see a green apple if not all ravens are black. The answer? The probability doesn't change much, because apples, whether green or red, exist independently of ravens. Yet still, ever so slightly, seeing a green apple shifts the needle toward confirming that all ravens are black. This microscopic, almost imperceptible reinforcement is what's so counterintuitive and disturbing. You begin to realize our methods of confirmation aren't just based on relevant evidence. They're based on logical consistency across the entire universe of observations. That means your hypothesis about ravens is entangled with every object in existence. It's the butterfly effect of epistemology. Here's where the paradox takes a philosophical turn. If science works by gathering confirmatory evidence, and if that evidence includes totally irrelevant seeming observations, like green apples or blue cars, then what does it really mean to say a theory is well supported? Are we drowning in a sea of meaningless confirmations that we mistake for truth? The Bayesian view tells us yes and no. Yes, because evidence that seems irrelevant may still logically shift probabilities. And no, because not all evidence carries the same weight. Bayesian analysis allows for degrees of belief, and most non-black non-ravens, like a field full of grass, don't strongly move the needle. A green apple confirms the raven hypothesis, but barely. A black raven? That's heavy evidence. But now, imagine building an AI scientist, one who follows logic and Bayesian principles perfectly. Would you really want it drawing conclusions about birds based on fruit? And what does that say about our trust in data-driven systems? The paradox of the raven is not about ravens. It's about how we know what we know. It challenges the very structure of reasoning, forcing us to ask, what counts as evidence? What is meaningful confirmation? Can logic and intuition ever be reconciled? And when they diverge, which one should we trust? This paradox tears open the fabric of scientific inference. It reveals that knowledge isn't a clean, straightforward road. It's a tangled, probabilistic web, one where everything connects, even the absurd and irrelevant. And perhaps most haunting of all, it reminds us that logic alone cannot always tell us what matters. In the realm of Bayesian physics and probabilistic thinking, certainty is a myth. Every green apple is a data point. Every raven, every observation is part of the calculation. But the question remains, how far are we willing to stretch reason before it snaps? The next time you see a fruit stand filled with colorful apples, pause. You might be, in some infinitesimal, cosmic way, confirming a law about ravens. Imagine sitting in a room with a gun pointed at your head. But this isn't just any gun. It's connected to a quantum device that measures the spin of a subatomic particle. If the spin is up, the gun clicks harmlessly. If it's down, it fires. Now, imagine repeating this experiment over and over. One version of you hears only clicks. Another doesn't make it. Over time, the only version of you that continues experiencing consciousness is the one that survives, every single time. Welcome to one of the most disturbing and fascinating ideas in quantum physics, the quantum suicide and immortality paradox. This thought experiment takes us deep into the strange and terrifying implications of the many worlds interpretation of quantum mechanics, an idea that proposes that every possible outcome of every quantum event actually happens, not just in theory, but in an ever-branching multiverse of realities. When a particle spins up, one universe is born. When it spins down, another. And when your life depends on that spin, only the version of you in which you survive is the one that continues experiencing life. Now, here's where things start to unravel your mind. If you truly accept the many worlds view, then in some branch of the universe, you never die. No matter how many lethal scenarios you face, quantum randomness always allows for some sliver of possibility in which you survive. And because your consciousness is tied to your subjective experience, you only ever remain aware in the worlds where you live. To everyone else, you're gone. But from your own perspective, you're immortal. At first, this sounds like a twisted form of eternal life. But when you start peeling back the layers, the horror sets in. This isn't real immortality. It's quantum immortality. You might survive a crash, an explosion, a disease, a firing squad, not because you're lucky, but because in the endless branching timelines, some versions of you always make it through. But the cost? You exist in increasingly improbable and nightmarish realities. Each escape leaves you more broken, more isolated, trapped in a timeline where everyone else is gone and you're the last remnant of a quantum roll of the dice. Let's bring in Schrödinger's cat for a second. In that thought experiment, a cat is both alive and dead until observed. The observer collapses the wave function, but in the many worlds view, there is no collapse, just a split. One world with a live cat, one with a dead cat. Quantum suicide turns you into the cat. You don't collapse, you diverge, you survive, always, but only in your own consciousness. From a physics standpoint, this is built on the probabilistic nature of quantum measurements and the idea that consciousness follows continuity. From a philosophical standpoint, it tears open questions about identity, death, and the limits of reality. Are you truly you if every choice you make spawns infinite versions of yourself? And what happens when you run out of universes to survive in? Now think about this. In some branches of the universe, you're rich, powerful, successful, maybe even a hero. In others, you're isolated, maimed, barely clinging to life. Quantum immortality doesn't promise a better life, just a longer one. And not in the way you might hope. There's no magical healing, no reset. You age, you decay, you suffer, but you never stop. And there's something deeply tragic about that. It's like a curse disguised as a gift, a deterministic trap wrapped in quantum freedom. Of course, this is all theoretical. We don't have proof that the many worlds interpretation is true. It's just one interpretation of quantum mechanics among many. But it's one that, if true, has terrifying implications for what it means to die and to live. Here's a chilling question. If you were trapped in a situation where your death was inevitable in all but a 1 in a trillion outcome, would you try it, knowing that somewhere, somehow, you'd make it through? And even if you did, would that really be a victory? Some argue that quantum suicide and immortality exposes the absurdity of the many worlds theory, pushing it to its limits. Others see it as the ultimate expression of what quantum reality could mean, how personal experience may defy everything we think we know about finality. In the end, the paradox isn't about whether you die or live. It's about the boundary between consciousness and reality, between probability and certainty, between science and something that feels dangerously close to myth. And if somewhere out there, some version of you is hearing this narration for the 100th time, maybe they've never stopped listening. Maybe they never could. The universe, it's vast, it's mysterious, and it's full of wonders we can barely comprehend. But here's the question that no one seems to be able to answer. Why does anything exist at all? We often take existence for granted, assuming that the world around us is just there. The stars, the planets, the atoms, even ourselves. All of it seems like it has always been here, part of the natural order. But when you pause, when you push your mind beyond the limits of the everyday, the question arises, why? Why does anything exist instead of nothing? This isn't just a metaphysical question. It's a deep existential paradox that has troubled philosophers, scientists, and theologians for centuries. It's a paradox because it cuts to the heart of reality itself. It challenges the very foundation of our understanding of the universe. Let's start by imagining the nothingness. What does it mean for nothing to exist? It's not emptiness, it's not a vacuum, because those things are still something. Nothing means the absence of everything. No space, no time, no matter, no energy, no laws of physics, no consciousness to question it. In this nothingness, there is no something to question why there is anything. There's just nothing. But here we are, a universe of something. It's a contradiction that stares back at us from the edge of all reason. One of the most famous figures to grapple with this question was Leibniz, a German philosopher in the 17th century. Leibniz coined the question that would haunt generations of thinkers. Why is there something rather than nothing? It's a simple question, but it's profound. To him, the fact that anything exists at all is a mystery that needs explaining. It's an issue of cosmic necessity, a fundamental problem that has no straightforward answer. And yet, we live in a universe that is defined by its existence. Why? For all the theories we've developed in physics, from the Big Bang to the multiverse, none can answer the core question of why anything exists. We can dive into the fabric of reality. We can look at quantum mechanics, with its strange behavior of particles popping in and out of existence. Quantum fluctuations are a phenomenon where energy seemingly appears from nowhere, only to vanish again. But here's the catch. These fluctuations are still something. They're not nothing. They're something that emerges for a brief moment and disappears, but it's still something. Then, there's the Big Bang. The universe as we know it exploded into existence from an infinitely small point. But what was before the Big Bang? What caused this explosion of everything? Some physicists point to the concept of singularity, a point of infinite density and temperature. But that only pushes the question back further. What caused the singularity? What caused the cause? It's like a never-ending loop of causality that never truly begins. We can't escape the paradox. The very fact that the universe exists seems to imply that it must have had a reason, yet there is no clear cause we can point to. Why does anything exist at all? Some physicists have tried to answer this with the concept of quantum fluctuation. The idea that the universe might have arisen from a random fluctuation of quantum fields. But again, we're faced with the same problem. Why did the fluctuation happen in the first place? Some answers attempt to link this paradox to the anthropic principle, the idea that the universe must exist in such a way that life can emerge in it. But this doesn't really answer why the universe exists at all. It only explains why the universe allows life to exist. But the existential question remains. Why is there something rather than nothing? Let's delve into some deeper, more abstract ideas. One such answer comes from philosophical idealism, a school of thought that suggests consciousness itself could be the fundamental substance of the universe. According to this view, reality doesn't exist independently of consciousness. Instead, consciousness creates reality. In this framework, the universe exists because it's being perceived. It exists for the mind to experience. But even this doesn't answer why consciousness itself exists, or why consciousness would need to create the universe. Other theories try to answer this paradox by looking beyond our universe entirely. The multiverse theory suggests that our universe is just one of many, each with its own set of laws of physics. In this scenario, we live in one of the universes where conditions just happen to be right for existence. But that doesn't provide a real answer. It just extends the question into a larger scale. Why do all these universes exist in the first place? And what, if anything, created the multiverse? Then there's the even more radical idea that we might live in a simulation, that the universe is a computer-generated construct created by some advanced civilization. In this case, the question shifts to, why does the simulator exist? What purpose does it serve? But even in this theory, the paradox is only reframed. It still exists. At its core, the paradox of why anything exists at all is rooted in our limitations as conscious beings. Our minds are bound to a physical reality where we experience cause and effect, where time has a direction, and where every effect seems to have a cause. But the question of existence itself, of why there is something instead of nothing, remains outside of our grasp, beyond the limits of reason and logic. Maybe it's something we'll never fully understand. Maybe the answer is beyond physics, beyond philosophy, beyond the human experience. But perhaps, in trying to understand why anything exists, we'll begin to glimpse the edge of what it means to be conscious, to exist, and to question the nature of reality itself. As we wrestle with the question of existence, one thing becomes clear. The fact that we're here, that we're able to ask these questions, is perhaps the greatest mystery of all. It is the question that defines everything we know and everything we don't.